The special theory of relativity saves physics. Physicists of the 19th century faced a serious question in their research. Why do matter and light behave differently? Einstein's special theory of relativity solved this mystery by altering classical notions of time and space. In Italy, during the 17th century, the brilliant Galileo Galilei, who lived in the 16th and 17th centuries, discovered a principle characterizing the motion of matter, which would later be called the principle of relativity. In 1905, the young Einstein managed to extend this principle to a completely new area, the propagation of electromagnetic waves, not only in the realm of visible light, but also in invisible radiations, infrared, ultraviolet, and radio waves. Einstein established the defining role of the principle of relativity by developing Galileo's conclusions, while simultaneously rejecting the theory of the greatest scientist of the Renaissance that described kinematics. This branch of physics describes the motion of free objects that are not subject to any forces, in contrast to dynamics, which describes motion under the influence of various forces. Einstein replaced Galileo's kinematics with his own new kinematics. He developed a new theory, radically discarding previous notions of space and time and replacing them with spacetime, a singular entity with very strange properties. So, what does the principle of relativity, first discovered by Galileo and later developed by Einstein, consist of? Both formulated it as follows. The laws of physics are stated the same way for different observers. Physicists conducting measurements who are moving relative to each other. However, there is one essential and important condition for this principle to hold. The observers must be inertial, meaning they are not subjected to external forces and are moving solely due to their own inertia. For example, this principle excludes an astronaut launched into space using rocket engines, or a planet pulled into orbit around the sun by gravitational force. All inertial observers move uniformly relative to each other, that is, in a straight line and at a constant speed. This, by the way, outlines another principle, the principle of inertia. An observer at rest, who is not moving, is also considered inertial. Thus, the principle of relativity requires that all laws of physics be formulated for an inertial observer as if they are at rest. This encapsulates the essence of the principle, which Galileo expressed in a beautiful formula. Uniform motion is equivalent to a state of rest. This approach defined the use of the term relativity. The principle demands that all inertial observers play strictly identical roles, so that the laws of physics are the same for everyone under similar conditions. It is impossible to distinguish an observer at rest from one moving uniformly. In other words, the only meaningful definition of motion becomes the motion of different observers relative to each other, and the expressions absolute motion and absolute rest are simply meaningless. They do not exist in nature. Galileo's principle of relativity became the foundation for Newtonian physics. It shows how these scientists interpreted the concepts of space and time in their theories. Einstein was able to extend this principle to the phenomenon of electromagnetism. The fundamental principles of electromagnetism were formulated by the Scottish physicist James Clerk Maxwell in 1806. He constructed a unified theory for electric and magnetic interactions, and Einstein's principle of relativity, applied to these phenomena, laid the groundwork for a new theory, the special theory of relativity. Like its precursor in Galileo, the new principle of relativity describes inertial observers moving uniformly, but it also takes into account electromagnetic interactions, which immediately changes the picture by eliminating the separate absolute concepts of space and time and replacing them with a unified spacetime. Furthermore, 10 years later, Einstein would extend these new principles to non-inertial observers and non-uniform motion. Thus, the principles of general relativity were formulated, examining the already curved spacetime. That was his mission. 1905 became a remarkable year. In 1905, Albert Einstein worked at the Federal Office for Intellectual Property in Bern. He had to assess the novelty and significance of the patent applications submitted to the office. "Without this job," he wrote, "I would have gone insane." Einstein enjoyed the material independence that allowed him to contemplate what interested him and published 5 fundamental papers that had a revolutionary impact on physics. It was truly a magical year. In his very first paper on a heuristic perspective regarding the emergence and transformation of light, he proposed the hypothesis of the existence of a quantum of light. This hypothesis became the foundation of quantum physics, and for it, he would receive the Nobel Prize in 1921, the only one throughout his scientific career. Remarkably, 2 other papers, New Definitions of Molecular Sizes and The Motion of Particles Suspended in a Resting Liquid Required by the Molecular Kinetic Theory of Heat, are related to the theme of his doctoral dissertation. He explained the phenomenon of Brownian motion, the completely chaotic movement of particles in a liquid colliding with the molecules of the liquid. This conclusion confirmed the hypothesis of the existence of atoms and molecules. The conclusions of the 4th paper on the electrodynamics of moving bodies formed the basis of the special theory of relativity, while the 5th paper, Does the mass of a body depend on its energy content?, gave rise to the most famous formula in physics, E equals mc squared. But how did Einstein manage to do without time, thanks to the astonishing unresolved problem that arose from Galilean kinematics? The latter, as we have mentioned, describes the motion of free objects that do not engage in any interactions. Such motions, therefore, cannot depend on anything other than the inherent properties of time and space, and kinematics emerges as a manifestation of the properties of space and time and the interactions that connect them. Galileo's or Newton's kinematics has one important limitation. The speeds of the objects in the problems it considers add up linearly, arithmetically. If you walk at a speed of v1 in a train moving at a speed of v2, then relative to the tracks, you are moving at a speed of v1 plus v2. This obvious and a priori conclusion, however, led to a scientific crisis in physics. Even in the 19th century, it was gradually noticed that light does not obey the laws of Newtonian mechanics. Instead of adding its own speed to the speed of the light source, light always moves at a constant speed. This discrepancy could not be ignored. It was confirmed in 1887 by the landmark Michelson-Morley experiment. The experiment convinced the scientific community light does not obey the laws of kinematics, unlike matter. But how to interpret this discrepancy? If we consider that kinematics reflects the fundamental relationships of space and time, how can the properties of space and time differ depending on whether you are considering light or matter? This was a genuine mystery. In the same 19th century, physicists believed that light required some medium, occupying all of space, to propagate. They called this medium the luminiferous ether. Light appeared to be a wave, similar to waves on water, and the latter propagate in a specific medium. Scientists assumed that ether could play for light the same role that, say, the sea plays for waves. However, if light propagated in ether according to the laws of Galilean and Newtonian mechanics, its speed would be the sum of the speed of the light source. Physicists believed that it was possible to determine the speed of the Earth's motion through ether by measuring the speeds, a priori assumed to be different, of several beams of light. One beam would propagate in the direction of the Earth's rotation around the Sun, while another would propagate against or perpendicular to the orbit. In 1887, American physicists Albert Michelson and Edward Morley used an interferometer, a highly precise instrument invented by Michelson, to conduct this experiment. The result was negative. No matter which direction the light beam was directed, the speed of light remained unchanged, and no signs of ether wind were detected. Some physicists speculated that there was an answer to the mystery. At the beginning of the 20th century, George Fitzgerald, Hendrik Lorentz, and Henri Poincaré independently proposed formulas to solve this inconvenient problem. They modified the kinematic principle of adding speeds, suggesting that instead of adding speeds arithmetically, they should undergo a mathematical transformation that would later be known as the Lorentz transformation. The formula accounted for the peculiarities of the behavior of matter and light. In the first approximation, when the speeds of the objects under study are small, the result of the transformation is almost equal to the sum obtained through classical arithmetic addition. This rule applies to all objects from our everyday life. For them, Galileo's formula gives quite adequate accuracy. However, if one of the two speeds equals c, that is, the speed of light in a vacuum, the result remains equal to c. Thus, it turns out that the speed of light is invariant and constant. Furthermore, the formula implies that no material object can reach this speed c, and it has become an absolute limit. Thus, the new formulas allowed for a solution to the problem concerning c and speeds. However, physicists found it puzzling how and why this formula mixed the coordinates of time and space. Moreover, it was astonishingly difficult for people to reconcile it with familiar notions of time and space, and the formula remained an unresolved puzzle for scientists, eluding any attempts at interpretation. Up until 1905, Einstein realized that it required a complete revision of classical notions that had been in use since the time of Galileo and Newton, and primarily a rejection of the conventional concepts of time and space. Shortly thereafter, the German physicist Hermann Minkowski, who had been Einstein's teacher, proposed the new concept of spacetime, which became the ideal backdrop for formulating new kinematic transformations and Einstein's special theory of relativity. In 1676, while observing the moons of the planet Jupiter, the Danish astronomer Ole Rømer was the first in history to understand that light propagates at a finite speed. But at that time, nothing was known about the fact that this speed was somehow special. Only in the 19th century did changes occur in scientists' perceptions. Maxwell discovered that light has an electromagnetic nature. The most revolutionary discovery was the realization that the speed of light does not add up with other speeds, as happens with material objects, but remains invariant and constant. Albert Einstein explained all these peculiarities in the special theory of relativity. The speed of light as a constant, denoted in physical formulas as c, is an inherent property of spacetime, and any other electromagnetic radiation propagates at the same speed c. Today, physicists consider this speed a fundamental constant of the universe, a characteristic of spacetime itself. We are accustomed to thinking that c is approximately 300,000 kilometers per second, or 300 million meters per second. However, the theory of relativity unifies space and time. Our habit of measuring duration in seconds and length in meters with different units begins to seem quite absurd in light of the new theory. According to Einstein's theory, measuring length and duration in the same units proves to be quite logical. We rightly do this. Astronomers measure distances in light hours or light years. In this unified measurement system, a light second and a second are simply equal to 1. This system is very convenient for physicists, allowing them to avoid using gigantic numbers, but it is completely impractical in everyday life. We still use meters and seconds, and the constant c serves as a conversion factor between units of measurement. These conclusions were taken into account in 1983 during the definition and standardization of length. According to the official decree of the International Bureau of Weights and Measures, the unit of length is considered to be the meter, derived from it, and is defined as approximately 1/300 millionth of a second. It takes time to get used to this. Einstein was one of the first to sense that it was necessary to abandon the concepts of absolute space and absolute time introduced into physics by Newton. Our perception of a unified space and unified time is merely an illusion. In reality, they have no physical meaning. What we perceive as the flow of time should be understood as the flow of individual time, which is significant only for a specific person and not for anyone else. This time is neither absolute nor universal. Nevertheless, on Earth, the personal time of individuals does not differ much from one another. This allows us, Earthlings, to combine time into a single timeline and refer to it as universal time. How might this conceptual revolution reflect on our everyday understanding? This remains to be understood. Our experience interacting with the phenomena around us is quite limited, considering that we are dealing only with very minor perturbations of spacetime. These perturbations can be neglected on the scale of the Earth, and the system, including our Earth, or even the solar system, and of course humanity itself, can be viewed as a whole microscopic physical body. In this approximation, the singular unified time associated with this body is the time of humanity as a whole. This is what we call universal time. This works excellently in our familiar lives, and universal time is quite applicable for measuring many different physical parameters that do not require special precision. However, as soon as the required measurement precision increases, it becomes impossible to lump all earthly beings and objects together as if they truly constituted a single physical body. It is impossible to assume that the common time, universal or otherwise, flows the same for everyone. And regardless of the required precision, this hypothesis completely fails when it comes to objects moving very quickly, such as microparticles in accelerators or cosmic radiation. It, too, consists of particles accelerated by natural processes in space. The precision of the parameters required for our everyday life does not allow us to notice that, in reality, there is no single time on Earth. However, it is essential to understand that at a fundamental level, at the level of theoretical concepts, natural phenomena cannot be connected with the notion of a single time that would flow uniformly for all bodies. This concept is now definitively outdated. It is no longer used in theoretical physics or philosophy that describes the nature of things. Only individual time remains. It has become a concept related not to describing how the world is structured, but to how we perceive it. At the same time, fortunately, the foundation upon which all events unfold does exist, and it has already been given a sufficiently comprehensive definition. This is space-time. It is common to all physical bodies, all observers, and all physical phenomena. We all exist in space-time, not in space and time. Einstein's new theory, the special theory of relativity, is formulated precisely for space-time. The laws of physics formulated for space-time magically take on a simpler and more elegant form. For example, the combination of speeds in the Lorentz formula, which was incomprehensible to physicists at the beginning of the 20th century, transforms into a simple rotation in space-time, meaning a four-dimensional embodiment of ordinary three-dimensional rotation. A change in speed in the conventional sense in space-time becomes an angle. Kinematics, previously perceived as a change in parameters over time, becomes the geometry of space-time. Let us recall, for instance, Newton's formulation of the principle of inertia, the property of a body to maintain its state of rest or uniform straight-line motion. In the special theory of relativity, the principle is defined as the property of a body to maintain straight-line motion in space-time. We achieve simplicity in formulations and concepts. Albert Einstein's theory, as it turned out, simplified the formulations of the laws of physics. Of course, this alone does not prove its correctness, but many physicists, including Einstein himself, have always believed that simplicity and clarity of a universal theory are signs of its validity. Certainly, no one doubts, and Einstein always insisted on this, that the ultimate criterion for the correctness of a theory is experiments. Elegance and simplicity are not sufficient for any theory to accurately describe the world. The rules of physics are quite strict. The special theory of relativity has undergone complete experimental verification. Mathematically, space-time has a four-dimensional essence. It can be viewed as a generalization of the concepts of surface, 2 dimensions, or space, 3 dimensions. Mathematicians refer to such generalizations as manifolds. The use of this term helps avoid formulations like four-dimensional space, which can easily lead to confusion. The essence of space-time is that it possesses a clear geometry from which the peculiarities that seem to arise in the theory of relativity follow. First and foremost, what mathematicians call the metric, a mathematical tool that allows for measurements. If we can measure angles and distances in ordinary space, known as Euclidean space, it means it possesses a metric known as Euclidean. In any case, the geometry of space-time allows for the definition and measurement of both distance and angles. In fact, the term distance is not entirely suitable for describing space-time, as it suggests cosmic distances measured in space. It would be more accurate to refer to them as metric intervals. In ordinary space, any segment of a curve has a length defined based on the metric of the space. Similarly, in space-time, any segment of a curve is characterized by a specific value of the metric interval. However, as we shall see, space-time allows for the existence of various types of curves. The most interesting ones are those that represent the history of a process. These are temporal curves, and their length or metric interval represents the duration of the process's history, the duration experienced and measured by the one living in that history, which we consider its own duration. Notice that we do not even mention the concept of time. We will return to that. The geometry of ordinary space is called Euclidean, while the geometry of spacetime is referred to as Lorentz or Minkowski geometry. Lorentz and Minkowski played significant roles in the creation of the special theory of relativity. Instead of the term geometry, it would be more accurate to use the term metric geometry in this case. World lines in spacetime are events. Newtonian physicists consider events to occur at a certain point in space, localization, and at a specific moment in time, date. Physics primarily investigates events, such as particle collisions or the emission or absorption of photons of light, but it is also interested in processes that we, humans, call histories. As mentioned earlier, any material body, particle, or object, as a physicist observer, lives through a history consisting of a continuous sequence of individual events experienced by it. This history can be referred to as its lifeline, or, using a special term, a world line. A segment of this line represents a piece of the history of a given object. If an event is a point in spacetime, then a continuous sequence of events is a curved lifeline traced in spacetime. Any material body, therefore, is represented by its own trajectory, consisting of points, that is, moments of life, experienced events. However, not every curve drawn in spacetime necessarily represents a world line. A world line is a very specific curve in Lorentz geometry that describes spacetime. This curve is called temporal. However, note that this does not mean that time exists separately in spacetime. Each segment of this curve, according to Lorentz geometry and metrics, has its own metric interval, generalized length, duration. Just as in ordinary, familiar Euclidean space, any segment of a curve has a length. However, in spacetime, a segment of a curve signifies the history lived by a certain object, and its length corresponds to the duration of that history. It is better to even call it proper duration, not just duration, to remind us that this specific value pertains only to the object in question and is not related to time as such. This proper duration, in the everyday sense, is what was felt and measured by the specific individual who lived through their particular history. Thus, each material body possesses its own world line. One could even say, reasoning about the kinematics of the process, that the theory equates a material body with its world line. This holds true for the general theory of relativity in cases where no forces act on the body. Its inertial line becomes straight. This formulates the relativistic version of Newton's principle of inertia. If we assume that the gravitational influence of other stars and planets can be neglected, we can consider the Sun as a normal body, and its world line as straight. But in reality, in the actual universe, practically any body interacts with other bodies. Every body is subject to gravity. However, a photon, whose trajectory we see as a beam of light, can be considered normal. The proper time experienced by a material body in a given history represents the metric interval of its personal segment of the world line that denotes this history. When we consider the duration of this segment as the length of a curve in spacetime, we understand that it only makes sense for the body in question to which this curve corresponds. It is its world line and no one else's. This is why we cannot speak of time in general terms, and this is why the word time is accompanied by the adjective proper. The proper time of observers, any of us, serves to fix the events of their own histories on their own world lines. These events occur where a specific observer is at the moment of observation, but they cannot serve to fix other events or histories occurring elsewhere and with another observer, as they simply cannot be defined there. An earthling cannot use their proper time, their own time segment, to fix what is happening on Mars. Einstein thus came to the simple conclusion that it is impossible to determine a common duration, let alone a unified time, for two different bodies. Measurements, of course, must possess high precision to avoid confusing the bodies. Alongside temporal curves in spacetime, there are light curves. They represent the trajectories of immaterial objects, the light rays, that is, the world lines of photons. They do not resemble ordinary temporal curves, as their metric interval is always equal to 0. Thus, the theory of relativity reflects the constancy of the speed of light. It follows that from the perspective of a photon, the moment of its creation, even if it occurred in a very distant galaxy, is immediately followed by the moment of observation. A photon has no duration. All directions are equal. A normal observer, that is, an observer not interacting with anyone or anything, moves in spacetime along a straight line, which corresponds to their constant speed. To change speed, some force must act on them, and they will immediately cease to be normal. Their world line will begin to bend. The conclusion is that a change in speed in spacetime corresponds to a change in direction, that is, a turn or rotation. Observers moving at different speeds can be represented as world lines in various directions. The angles between these lines indicate the relative speeds of the observers. The principle of relativity states that all directions of the lines have equal values. None of the directions plays a special role. Naturally, we would like to assign our world line a special significance. However, we do this when we use our universal time, but that is our subjective perspective. The result may be the designation of some object in the universe as special, in this specific case, ourselves, designating it as at absolute rest, while considering other bodies as moving relative to us. Such an approach fundamentally contradicts the principle of relativity. It could happen that everyone decides they have the right to declare themselves at rest, believing that only others are in motion. The impossibility of identifying any physical body or physical coordinate system as being at rest is an inherent property of spacetime and is called isotropy. The isotropy of spacetime is now considered one of the fundamental postulates of physics. Scientists also refer to it as Lorentz invariance, as it signifies the symmetry of all phenomena concerning rotations and turns in four-dimensional spacetime, which, let us remind you, are identified with Lorentz transformations. The results of the experiment conducted by Michelson and Morley can be interpreted as the first confirmation of this postulate. If the experiment had yielded a different result, it would have indicated that there exists a special direction in spacetime, and we could have named that direction time. Such phenomena would appear no less strange than having some special direction in space. True time does not exist. We often hear and read. Of course, after Einstein created the theory of relativity, time flows the same for everyone. This is a mistaken interpretation of the term relativity. As we have established, the concept of time does not actually exist at all. The theory allows for the use of individual durations for each observer, but they are significant only for the specific observer. they can use them to calculate their proper time, measuring these individual durations starting from a moment they arbitrarily designate as the starting point, since the day of the storming of the Bastille, from the moment of birth, and so on. My proper time flows for me just as the proper time of any other observer flows for them. Trying to oppose them makes no more sense than attempting to compare the distance in kilometers between Paris and Lyon with the distance in kilometers between Los Angeles and San Francisco. Additionally, we cannot provide a definition that would have any meaningful significance for the concept of time. In the future, we will see how to practically define concepts that are more or less, with some assumptions, close to it. My proper time is defined where I am and nowhere else. In some cases, I can extend its significance to places with different coordinates. In principle, this is possible, but it will always carry an artificial hypothetical nature. Such extensions do not correspond to any measurable quantities, nothing we could consider physically existent. It is merely a conditional designation of events that creates certain conveniences. What is referred to in cosmology as cosmic time allows for some ordering of events in the history of the universe. However, cosmic time does not correspond in any way to the durations of astrophysical processes. Thus, my proper time and my individual durations matter only to me, and I alone can measure them. I have no way to measure the duration of some process on the planet Mars, even if my understanding of Einstein's theory allows me to reconstruct that process based on a series of observations. So, proper time is what observers A and B have nothing in common. There is no section of space-time where we could define them simultaneously, except in the situation where A and B are directly together. And there is no way to compare them. It is also important to emphasize that in any case, TA flows from A's perspective just as TB flows from B's perspective. The proper time of each flows equally, even if no one has ever attempted to determine some global time. This complex idea is crucial. In reality, there is no slowing down of time, no shortening or stretching of duration. An observer can measure the duration d0 of some history or process relevant to them, that is, part of their world line. The observer does not have access to the flow of that duration. They cannot measure it, but they can observe history, A, and measure their own duration. They measure not the duration of history, A, which does not happen with them, but the duration of their own observation in history A. This observation becomes part of their own history, history B, and has its own duration, which has nothing to do with dA. In astronomy, such relationships between two observers are usually referred to as redshift, most often. Let us imagine, for example, a supernova explosion that lasts a week. The explosion would demonstrate its own proper duration, which simultaneously corresponds to the operational duration of the DSN clocks, that is, 1 week. We can also observe this explosion between the signal received at the observatory at the beginning of the explosion and the signal that passes at the moment of its conclusion. There will be a period of DPS, the duration of the process that we experienced, which our clocks measured, and this duration is not exactly equal to 1 week. The relationship between durations defines the shift, or redshift. It becomes 0 only if the proper durations are equal, which is merely a special case when the coordinates of the observer and the observed object coincide. My own time is accounted for along my world line. Measuring time in everyday life does not possess the necessary precision, which is why we often confuse our own world line with those of our neighbors. Due to the insignificance of the deviations of my own time from that of my surroundings, I can neglect the differences in duration and extend my own time to those close to me. This is precisely what we have come to call time. In fact, it is a total illusion to assume that a common time truly exists, as it seems quite real. And this illusion allows us to use Newtonian physics without issue. However, such a situation is an exception on the scale of the universe. In astronomy, in the theory of electromagnetic fields, in satellite navigation, and in communications between Earth and space probes, particle physicists cannot employ the concept of common time. Nonetheless, this concept is hard to ignore, as it is firmly entrenched in public consciousness. The special theory of relativity caused time to disappear, so it is not surprising that most properties related to our understanding of time have also vanished. Time frames, concepts of simultaneity, precedence, past, present, and future in a chronological sense. The cleansing was powerful. However, during this process, a more fundamental essence of the universe was revealed. Causal relationships lie at the heart of space-time. We can no longer refer to one event as simultaneous, preceding, or subsequent to another in a chronological sense. However, we can determine whether there is a causal relationship between events or not, and this in a strict mathematical sense. If there is a relationship, then one event is the cause and precedes the other. At any moment, all the rays of light that an object can emit form its future light cone. At any moment, all the rays of light that an object can receive form its past light cone. One event may not precede another chronologically, as chronology no longer makes sense except under extremely local and highly subjective circumstances when material bodies move at immense speeds close to the speed of light. The properties of spacetime begin to manifest as so-called relativistic effects. They clearly demonstrate that there is no single time and can sometimes confuse people unfamiliar with physics. Astrophysics, cosmology, and the physics of particles moving at high speeds in space or in the laboratory are replete with such examples. Take cosmic rays, for instance. These electrically charged particles, possessing high energy, travel through space. When their trajectory passes near Earth, they interact with air atoms in the upper layers of the atmosphere at altitudes of several tens of kilometers. Some collisions between atoms and particles release enough energy to create new streams of particles. Among them are muons, particles similar to electrons, but 207 times heavier. Muons are unstable. Their average lifespan is merely 1.5 microseconds from creation to decay. Originating in the upper layers of the atmosphere, muons reach the Earth's surface at speeds close to the speed of light. Some enter a detector, and a particle physicist observing from Earth can measure the lifespan of muons on their way to Earth until they hit the detector, which lasts about 10 microseconds. This is not an anomalous result. What we call the lifespan of a muon, 1.5 microseconds, is its proper duration of existence. Only it can measure or feel it from its own perspective. No observer has access to it unless they fly directly with the muon. All the observer can measure is the duration of the observation from their side, how long they observed. The observer experiences their own flow of history, but there is nothing in common between them. Neither duration is time. The concept of proper duration has sparked heated debates. One of the most famous discussions was initiated by the French physicist Paul Langevin in 1911, just a few years after the publication of Einstein's theory. The physicist proposed a thought experiment involving two twins, one of whom remains on Earth, while the other flies into space on a high-speed rocket. After several years, he returns to Earth and discovers that his brother is older than he is. This situation seems paradoxical at first glance, but it can be simply explained. In reality, each of the brothers lives his own story, distinct from the others. These stories are represented by two different segments of curves in spacetime. Even though they have the same beginning and end, these two different segments have different lengths, as they correspond to two different proper durations experienced, felt, and measured by two different individuals. These curves do not depend on each other. They have different characteristics. To answer a frequently asked question, it is essential to understand that the stories of the twins are not identical. There is no symmetry between them. While one twin is in flight, the world lines of the brothers differ, resulting in different segments experienced. Upon return, it turns out that the traveling twin has aged less than the one who lived on Earth. In fact, the traveling twin experiences repeated accelerations and decelerations while taking off from Earth, turning in space, and landing, while nothing similar happens to the Earth-bound twin. In other words, the traveler's history can be represented as a broken or curved world line, as acceleration in spacetime can be represented as a change in direction, and vice versa. The history of the stay-at-home twin is inertially depicted as a straight line between two event points, which can be marked as the departure of the traveler and the new meeting of the brothers. The length of the proper duration of the straight segment differs from the length of the segment of the curved or broken line. The general theory of relativity reveals the geometry of the universe. For Newton, gravity was a force acting in absolute space and time. Einstein, in creating the general theory of relativity, transformed it into a geometric characteristic of the universe. In 1905, when formulating the special theory of relativity, Einstein understood that it did not describe the universe exhaustively, although it explained much. The special theory did not describe the phenomenon of gravity, for example, why bodies fall to Earth while planets orbit stars. This is why Einstein began meticulous work on the theory of gravity, developed by the great Newton in the 17th century. Although it explained much, over time, questions accumulated regarding it. Isaac Newton's major work, Mathematical Principles of Natural Philosophy, Philosophia Naturalis Principia Mathematica, was published in 1687. It laid the foundation for all modern physics. Newton was the first to introduce the concept of time and space, which physicists used for over 200 years. One of his primary achievements was the introduction of the concepts of universal gravitation. It received this epithet because it acts uniformly everywhere, constantly, and on all bodies in the world. More precisely, this means that the weight of all earthly bodies, as well as the motion of the Moon, Earth's natural satellite, planets, comets, and stars in the sky, is governed by the same gravitational force. For the 17th century, this was a true scientific revolution. Newton's fundamental law of universal gravitation states that all bodies attract each other with a force directly proportional to the mass of each and inversely proportional to the square of the distance between them. One could say that Newton viewed gravity as something that causes bodies to change their motion in space, pushing them toward each other with an acceleration that would not occur if gravity did not exist. In practice, Newton's theory works remarkably well. It explains both the falling of bodies to Earth and the motion of planets and satellites, along with the fact that their orbits have an elliptical shape, which Johannes Kepler discovered at the very beginning of the 17th century. Confirming Kepler's laws, Newton's theory describes the parameters of these ellipses. It predicts the periodic return of comets and even more. By studying the trajectory of Uranus's orbit and assuming gravitational influence from another planet, the French scientist Urbain Le Verrier discovered the planet Neptune in 1846. Certainly there was no reason to doubt such a solid theory which seemed to govern bodies. Nevertheless, Einstein has doubts about the law of universal gravitation as well as many others from a conceptual and philosophical perspective. The matter took a new turn as physicists faced serious problems that did not fit into the old theory despite its high effectiveness. To embark on intellectual adventures lasted a decade. The first flaw of physics was the action of gravity at a distance. Objects act on each other without any contact, having no means to transmit mutual influence. It resembled some sort of magic. Newton, of course, mentioned a medium he called the gravitational ether, which he believed served to transmit interactions. However, it did not fit into any flaw in Newton's physics that Einstein identified was the concept that underpinned Newtonian calculations. This space cannot be seen, cannot be felt, and therefore cannot be experimentally proven to exist. Isn't all this a reason to doubt its existence? Moreover, Leibniz, a contemporary of Newton, already suggested a certain relativity of the concept of space. Leibniz's space was not so of the objects it contains, but rather a collection of all the relationships between objects. This led to some very curious consequences. Truly empty space containing no objects could not exist. The concept proposed by Leibniz became a subject of reflection and discussion for the philosopher and physicist Ernst Mach. Their works, among others, had a significant influence on Einstein during his work on the theory of relativity. There was another mystery in Newton's theory that troubled Einstein, the equivalence principle. Galileo had already noted certain aspects of the action of this principle, and Newton included the principle in his theory but could neither confirm nor convincingly explain it. Einstein focused on this problem and used it as a guide in his reflections. He not only took the equivalence principle into account, corrected formulation, the starting point of the general theory of relativity. This principle allows for the prediction of certain phenomena without making any special calculations. For example, its immediate motion can be seen in the deflection of light rays, which we will discuss. This famous principle consists of. It was first formulated as the principle of free fall without explanation by Galileo. If several objects are dropped simultaneously from the same height, they will all experience the same acceleration and fall to Earth at the same time, regardless of their nature or composition. A pebble, a bottle. It may no different. They will all. If our everyday experience contradicts this principle, it is only because different objects experience different air resistances which act on them as an external force. This principle can be reliably tested in a vacuum. It is astonishing how Galileo was able to formulate the principle, as he could not observe it directly, despite legends. Leaning in his theory of gravity, Newton showed that the universe resistance to the fact the weight of objects is proportional to their mass, or more precisely, that inertial mass, which resists the motion of a body, is identical to gravitational mass, which, on the contrary, underlies the motion of a body under the influence of gravity. It is this compensation of both masses of the action of the
Principle of free fall.
Einstein endowed the principle with a fundamental character, making it the starting point of the general theory of relativity. He formulates it for a specific case, that is, for an observer making measurements directly at the moment of their presence, as follows. It is impossible to detect a difference between the phenomena of acceleration and gravity. They are fundamentally indistinguishable. Let us list the new conditions that were set before Einstein in his work on the theory. First and foremost, he wanted to extend the scope of the special theory of relativity to gravitational phenomena, which were not considered within it. Then he wanted to solve the mystery of the ether. How can gravity propagate in a vacuum? Finally, it was necessary to formulate the equivalence principle in a relativistic form, an extremely complex task. Nevertheless, the general theory of relativity was able to meet all the conditions and even exceed expectations. It was almost immediately subjected to numerous tests and demonstrated its complete superiority over Newtonian physics, predicting many previously unknown results. This task was accomplished while preserving the achievements of the special theory of relativity, the disappearance of absolute space and time, and the introduction of the concept of spacetime. Spacetime ceased to be merely a backdrop for matter. It became a dynamic medium interacting with matter, which also includes the application of the theory. Spacetime remains, but the geometry of this spacetime is more complex than that of Minkowski spacetime, where the special theories of relativity operate. Retaining four-dimensionality, this spacetime has a shape that mathematicians describe with a quantity known as curvature. Curvature can be thought of as a generalization of the concepts of surface curvature, or the curvature of some object. The curvature of spacetime corresponds to the distribution of mass and energy in the universe. The main idea of the theory of relativity is that gravity represents this same spacetime curvature. They are one and the same. It should be noted that this statement represents the final formulation of Einstein's equivalence principle. As Newton's theory described gravity, a massive body, like the sun, generates a gravitational force that acts at a distance on a body, like the Earth. This force imparts acceleration to the body, which alters its motion. According to the general theory of relativity, a body does not generate any force. However, its properties, mass and energy, act on spacetime, deforming it and thus creating curvature. One of Einstein's equations clearly describes this law. A body is not subjected to the influence of a force, but is compelled to move as if along a straight line, but on a deformed section of spacetime. That is, it is compelled to follow the curvature, moving along a bent trajectory, traversing along the natural curvatures, mimicking their shapes along its path. These lines are called geodesics. When curvature equals 0, the line becomes simply straight. However, there are no straight lines in spacetime. Geodesic lines play this role in spacetime. The Earth moves along the geodesic of spacetime, curved by the Sun, and all this is confirmed by calculations of orbits. Thus, the orbit takes on an elliptical shape. This is the foundation of the general theory of relativity. The concept of gravity is replaced by the geometry of four-dimensional space created by various bodies in the universe. But what geometry are we talking about? To understand this, some clarifications and specifications are needed. The geometry we study in school was created a very long time ago. All its postulates were developed by the ancient Greek mathematician Euclid, who lived around 300 years before our era. no more precise data has been found. The father of geometry, as he is often called, formulated 5 postulates, or axioms, that is, mathematical geometric laws that have no proofs but allow for the proof of all other laws of geometry. This theory is known as Euclidean geometry. Among these axioms, the last, 5th, has always played a special role since the time of Euclid. This is the axiom of parallel lines, which states that through a point not lying on a given line, one can draw one and only one line parallel to the given one. Many mathematicians believed that the 5th postulate could be proven using the first 4. If so, it would become a theorem and be excluded from the list. Attempts to prove it were made repeatedly over the centuries, and each time without success. Eventually, it was proven, but only in the 19th century, that the postulate is, in principle, unprovable. This meant that in theory, it could be discarded, replaced by the opposite assertion. Through a point not lying on a given line, one cannot draw a line parallel to that line. Or through a point not lying on a given line, one can draw many lines parallel to that line. These new assertions gave rise to new geometries, different from Euclidean geometry. The first scientist to see the possibility of creating non-Euclidean geometries was the German mathematician Carl Friedrich Gauss, who worked in this direction between the 18th and 19th centuries. Among the pioneers of non-Euclidean geometry, we can also name the Hungarian scientist János Bolyai. The main contributions were made by the Russian mathematician Nikolai Ivanovich Lobachevsky and his German colleague Bernhard Riemann. Lobachevsky initiated Lobachevskian geometry, or hyperbolic geometry, while Riemann developed elliptic geometry. Lobachevsky asserted that through a point not lying on a given line, at least 2 lines can pass that lie in the same plane and do not intersect it. Riemann derived several axioms. For example, through any 2 points, one straight line passes. Any 2 lines lying in the same plane intersect at one point. Any 2 planes intersect along one straight line. All these new geometries were useful in Einstein's theory, as they consider curves in contrast to Euclidean geometry. From this perspective, Euclidean space and Minkowski spacetime have 0 curvature. There are many options for describing space with an arbitrary number of dimensions, and to introduce the concept of curvature, mathematicians use the term manifold. Thus, a line, straight or not, is a one-dimensional manifold. A surface, plane, or sphere is a 2-dimensional manifold. Our ordinary space, the space of Galileo or Newton, is a 3-dimensional manifold, while spacetime is a 4-dimensional manifold. One can create geometry for 5, 6, or even n-dimensional manifolds, n being some whole number. Today, there are no technical obstacles to this, although it is unlikely that one can visualize them. Each manifold is characterized by a specific value of curvature. It is always 0 by definition for Euclidean spaces and differs from 0 for non-Euclidean manifolds. A sphere, the most ordinary with radius r, has a constant positive curvature equal to 1 divided by r squared. On the surface of a sphere, there are no straight lines. They are replaced by geodesics, which serve as the shortest distance between 2 points. 3-dimensional spherical space has a constant positive curvature, just like the 2-dimensional sphere. Hyperbolic space has a constant negative curvature and resembles a saddle. Flat space has 0 curvature, like a Euclidean plane. On a sphere, geodesics are great circles. They share the same center as the sphere. They wrap around it, and in this way, they act as straight lines connecting points. Two circles always intersect at two diametrically opposite points, so there are simply no parallel lines to a given line. The geometry of a sphere represents a special case of elliptic geometry. In contrast, hyperbolic planes are characterized by constant negative curvature, and one can draw an infinite number of parallels to a given line. Yes, it is not so easy to visualize hyperbolic geometry. In three-dimensional manifolds, similar structures exist: spherical space with constant positive curvature and hyperbolic space with constant negative curvature. The curvature of Minkowski spacetime, the four-dimensional space where the special theories of relativity operate, is zero. This is natural, as special theories do not account for gravity. But in the general theory of relativity, everything is different. As early as 1912, Einstein understood that his theory required non-Euclidean geometry. The space-time of the general theory of relativity is more complex. Its curvature changes from point to point depending on the bodies that fill it. It is indeed challenging to visualize space-time and its curvature. To ease their work, physicists sometimes conduct thought experiments, slicing four-dimensional space-time into three-dimensional spatial layers. Although the theory states that this does not necessarily have physical meaning, it is somewhat akin to a three-dimensional book consisting of two-dimensional pages, or as if we were viewing Euclidean space as an infinite stack of planes. In cases where the geometry of space-time is sufficiently accurate for weak perturbations, the picture is relatively easy to visualize. Despite the artificiality of such imagined slicing into layers, this method allows us to view the theory of relativity as dynamic. The layers can be interpreted as versions of space at different moments in time. Of course, the concepts of time and moment are not entirely strict, but we allow our imagination to roam. Space-time is interpreted in this case as the dynamic evolution of three-dimensional spatial geometry. Imagine a flipping book as a single page that simply changes over time. Each individual layer represents a state of space at a specific moment in its evolution. Just as we number the pages of a book, we can also number the layers of space, and this numbering will become another parameter helping to illustrate the process of evolution. It is entirely natural that this parameter is generally called time. For example, cosmic time in cosmology. Of course, this is a very simplifying language, as such a parameter, which helps navigate the dynamics of space-time, is quite distant from all the properties we usually associate with what we call time. However, we can come up with an infinite number of different arbitrary variations, and this will change nothing. What does this give us? We consider space-time as a whole. We examine space whose properties change over time, and this makes it much easier to imagine. Intuition suggests it is simpler to draw parallels with familiar knowledge and experience. However, be warned. Even if time resembles what we have come to call time, we must not forget that this is merely an artificial and arbitrary construct, not reality. Goodbye to problems. Ultimately, the general theory of relativity eliminated all the contradictions that remained after Newton's theory and troubled Einstein. The answers were more than impressive. First of all, the concept of absolute space disappeared. It was replaced by relativistic spacetime, all properties of which are determined by the matter and energy it contains. Again, there is no longer a need to imagine interactions at a distance. A body, like the sun, for example, deforms space-time around itself. This deformation propagates at the speed of light and results in all spacetime becoming deformed. This curvature is interpreted as a consequence of a certain elasticity of spacetime. We will see later that in some cases, this propagation of curvature can be registered in the form of what are called gravitational waves. The phenomenon of the constancy of the speed of light in a vacuum shows that this elasticity has a constant magnitude. Both statements are equivalent. Gravity has found its meaning. It is related to the curvature of spacetime. It is this curvature that plays the role of the elusive gravitational ether of Newton. More precisely, gravity is this curvature. Thus, planets orbiting the Sun merely follow the curvature that holds them. How can we test Einstein's theory? Physicists, like in other sciences, acquire new knowledge through constant interactions between theory and experiments or observations of celestial phenomena. In the case of astrophysics, if a new theory is confirmed by a large number of experimental results, both known for a long time and newly obtained, it has every chance of being accepted by the scientific community. But it becomes truly interesting when it can predict certain phenomena better and more accurately than other theories, or when it predicts results that do not follow from any existing doctrines. 3 classical tests for Einstein's theory. Results arising from the theory of relativity were tested both by comparison with already known data and through special experiments and original observations. 3 fundamental pieces of evidence for the correctness of the theory were obtained between 1915 and 1960 and entered the annals of scientific history. In our solar system, every planet orbits the Sun in an elliptical orbit. However, the position of the ellipses is not constant. The closest orbit to the Sun, the perihelion, shifts slightly each time a planet completes its orbit. This phenomenon is called the precession of the perihelion and is explained in Newton's theory by the gravitational influence of other planets. Astronomical observations confirmed Newton's conclusions for all planets except Mercury, the planet closest to the Sun. The ellipse along which Mercury moves slowly rotates. The perihelion, the point of the ellipse closest to the Sun, shifts with each successive orbit. This precession of the perihelion owes its existence in part to the curvature of spacetime near the Sun. The astronomer Urbain Le Verrier, famous for discovering Neptune through calculations, proved around 1840 that the precession of Mercury was too great, 574 arcseconds per century, that is, 0.16 degrees per century, if we accept that an arcsecond is equal to 1/3600th of a degree. Although Newton's equations yielded a result of only 43 arcseconds per century. Where did this deviation come from? It was small, yet still significant, as Mercury's orbits are located near the Sun. The perihelion of this planet is at a distance of 46 million kilometers from the Sun, while the perihelion of Earth is at a distance of 147 million kilometers. The gravitational field acts on it in a special way. From Einstein's perspective, Mercury orbits in the region where the mass of the Sun most noticeably curves spacetime, and it is this curvature that causes the precession of the perihelion, whose magnitude becomes much more significant than predicted by Newton's theory. The value was calculated by Einstein in 1915 and completely matched the results of observations, much to his delight. Thus, the theory passed its first test successfully, almost immediately after its creation, the deflection of light. As we have already seen, In the relativistic curved spacetime, there are no straight lines. Their role is played by other lines, geodesics. A moving object follows the geodesic naturally. For example, every body in the solar system, a planet, a comet, an asteroid, and so on, describes a geodesic line around the Sun. This is its world line, a curve in spacetime corresponding to the position of a particle in space at every moment in time. A body cannot move in a straight line, as it simply does not exist. But light rays also follow the lines of curvature created by massive objects, along geodesic lines in curved spacetime. In special relativity, there were special light rays. In general relativity, the same applies. A light ray follows a light geodesic. Just as in special relativity, such curves have zero length in relativistic geometry of spacetime. In other words, light does not experience any duration on its path, neither proper nor otherwise. The path of a light ray emitted by a distant star may pass near a very massive body located between the star and Earth, following the curvature created by that mass. As a result, the Earth observer perceives the light as coming from a completely different point than where the star is actually located. In other words, the position of the star in the celestial sphere appears shifted. However, as early as 1911, Einstein concluded that the deflection of light caused by the mass of the Sun could indeed be observed and measured. More precisely, the position of the star and the light. The light ray passes near the Sun, reaching Earth, and should be visually displaced relative to other stars observed simultaneously. Einstein even calculated the expected shift before he had fully formulated all aspects of his theory. However, how could such observations be conducted? It is well known that during the day, when the Sun is shining, the stars are not visible, especially those whose rays pass close to the bright star, where the brightness is most intense. The only way to observe them seems to be during a total solar eclipse, when the moon completely covers the solar disk. The sky becomes dark, and stars appear, albeit only for a few minutes. During the total solar eclipse on the 21st of August in 1919, German astronomers attempted to observe the phenomenon of light shift from Russian territory, but Tsar Nicholas II's scouts captured them before they could begin their work. After the war, British physicist Sir Arthur Eddington, who lived from 1944, was one of the first scientists to understand Einstein's theory and achieved positive results during the eclipse on the 29th of May in 1919. It is worth noting that the evidence required funding for 2 expeditions, the first to Príncipe Island off the coast of Africa, and the second to the town of Sobral in Brazil. The observed deviation was 1 74/100ths of an angular second, which corresponds to the angle of view of an object 1 centimeter away from a distance of 1 kilometer, and confirmed the validity of the general theory of relativity. For many years, this observation became the most convincing proof of the theory's accuracy. The microscopic deviation played a huge role. Any process, any phenomenon, any story has its own duration, but one can observe the process from the outside. The observer measures the duration of the observation of the process, but not the duration of the process itself. In everyday life, the duration of any process will equal the duration of the observation. It would not even occur to us to separate one from the other, and ultimately, this allows us to use the concept of a unified time, common to all, that is, our universal time. If it were otherwise, that is, if relativistic effects manifested at the level of human life, it would be difficult to schedule a meeting or not be late for a train. But in another reality, for example, for a rocket flying at immense speed, for cosmic rays, or, say, for microparticles, these quantities differ. If an observer moves quickly relative to the system they are observing, the values can differ significantly. The difference between the duration of the observation and the duration of the process taken as a unit is called the shift, often spectral shift, for reasons that will be explained. All of this was described in the special theory of relativity, which did not account for gravity, but took its final form in the general theory of relativity. The influence of gravity complicates the situation even further when the process occurs under conditions of gravity that differ from those in which the observer is located. This affects the difference between the duration of the process and the duration of the observation of it. Two observers, under the influence of gravitational fields of different intensities, for instance, one at sea level and the other at the top of a mountain, cannot synchronize their clocks, provided they have the highest precision, even while remaining stationary on Earth. In the solar system, gravity does not act very intensely, as stars like the Sun and bodies like the planets of the solar system do not possess very high density. The shifts caused by them are negligible, and most often these shifts can be disregarded, especially if ultra-high precision observations are not required. In practice, observers may consider their clock readings to be coinciding and claim that they are measuring time. However, what actually happens, for example, with two identical clocks set at different heights, clock H1 at the bottom and clock H2 at the top. Suppose they tick once every second. That is, they produce one tick per second. The observer at clock H2 measures the interval between ticks and finds that it is 1 second. The same observer can also observe the other clock H1, for instance, receiving light signals with each tick of H1. Thus, he can measure the duration separating the reception of two consecutive signals. This duration will not equal 1 second. Clock H2 measures it as 1 plus z seconds, and the difference z'd between the two durations indicates the so-called Einstein effect. It should be noted that both clocks do not change their rhythm and continue to tick every second in their own time. There is no expansion or contraction of time observed. Such assertions can sometimes be found in erroneous but widespread publications. In practice, the Einstein effect is observed and is subject to physical measurements during experiments with individual atoms, which can be regarded as natural, ultra-precise clocks. Atoms of different substances, such as hydrogen, helium, and others, emit and absorb energy in the form of light of certain wavelengths and frequencies when the appropriate physical conditions are created. The set of possible frequencies corresponds to the spectral line that an atom can absorb or emit, and constitutes a spectrum that exhaustively characterizes the atom. The period of oscillation or radiation is nothing more than the intrinsic duration between two maxima of the radiation frequency. All effects described for the intrinsic durations of different processes similarly manifest in the case of light emitted by atoms. An observer standing right next to the atom measures the period of the spectral line emission, that is, the intrinsic time of observation coinciding with the intrinsic time of the atom, and determines the standard value recorded in all textbooks on atomic physics. However, if his colleague observes the same atom from a distance, for example, from another point located higher in the gravitational field, he will receive a signal whose period will differ from the emission duration that can be measured on sight. He will multiply by 1 plus z. The shift z is called the spectral line shift. It took until the golden 5-year period from 1959 to 1964 for Einstein, who by then had already passed away, to measure the small magnitude of this shift. The first experiments were conducted in 1959 by American physicists Robert Pound, one of the pioneers of the phenomenon of magnetic nuclear resonance, and his student Glenn Rebka. They used 2 points with a height difference of only 22.5 meters, at the base and at the top of the Harvard University Tower. At the top, several iron atoms emitted radiation with a certain periodicity, characterized by a high energy level, while at the base, a very precise receiver captured it. Using a clever design, the physicists measured the microscopic shift caused by this micro drop of light in the Earth's gravitational field. As a result, the predictions of the theory of relativity were confirmed with an accuracy of 1%, which was a magnificent result of a clever experiment conducted using a very small height difference. This effect is also manifested when observing the Earth. The radiation of atoms located on the surface of the Sun, according to the general theory of relativity, shows that the measured period is greater than the period of emission that can be measured on sight. For each atom, there is a specific value of the difference, albeit very small, 1/1,000,000th of a second. This effect can be verified by observing atoms on the surfaces of other stars. All results consistently confirm Einstein's theory with an accuracy of 1/10,000th. Recent experiments have tested the equivalence principle since the time of Galileo. The equivalence principle had several versions by Einstein. This principle inspired the idea that gravity is equivalent to the curvature of spacetime. The so-called weak version of the universality of the principle of free fall for all bodies, established by Galileo, can be tested by comparing the acceleration of 2 bodies of different compositions falling from the same height. These tests allow for the measurement of the universal gravitational constant, denoted as g, used in Newton's laws. The first precise experiments to prove the equivalence principle were conducted between 1885 and 1890 by Hungarian physicist Alfred Rendon, using clever scales specifically designed for this purpose. He established that the acceleration of 2 bodies is equal to within 1/1,000,000th. Considering the precision of measurements, these tests were repeated with better results in the early 20th century. Physicists showed by 1910 that the acceleration of different bodies is equal to within 100,000,000th. In the 1980s, theories emerged suggesting the existence of a 5th force, in addition to electromagnetism, nuclear interactions, and gravity, which could affect the results. However, no deviations were found. Today, for example, the distance from the Earth to the Moon is known with an accuracy of 2 centimeters, thanks to micro-reflectors of light beams installed by astronauts of the Apollo program at various locations on the lunar surface. By carefully studying the changes in this distance, as well as the acceleration of the Moon in the Earth's gravitational field, scientists achieved measurement accuracy of 1/1,000,000th. However, scientists continue to achieve better and better results, aided by satellites placed in Earth orbit. For instance, one cannot overlook the European project Microscope, On the 25th of April in 2016, a microsatellite designed by the French National Center for Space Studies, CNES, was launched to observe the equivalence principle, according to which an observer cannot distinguish the effects of a gravitational field from the inertial force arising in an accelerating reference system. The motion of two mass of different chemical compositions on the satellite was measured over 2 years, and in the conditions of space, where any random fluctuations are excluded, the measurement of free-fall acceleration provides an accuracy 100 times greater than during Earth-based studies. The Italian project Galileo Galilei, developed by the Italian Space Agency, ensures measurement accuracy using the same method as the French microscope to 100 billionth. On our planet, many people use the GPS, Global Positioning System, navigation system daily. It allows for optimal route planning for cars, orientation in cities, exploration of unfamiliar areas, or navigation in open seas, all with an accuracy of several meters. It is a very convenient tool that many can no longer do without. GPS systems utilize a whole fleet of satellites. To date, at least 30 satellites orbit the Earth at an altitude of approximately 20,000 kilometers, equipped with atomic clocks. They emit very precise radio signals. The user's receiver receives signals from at least 4 satellites and determines the time it takes for the signal to reach them. It then calculates the distance to each satellite, and knowing their exact positions, computes its own location in space. Nothing complicated, one might think. However, Einstein's theory of relativity states that the proper time of the satellite does not coincide with the proper time of the receiver located on Earth. This problem can be addressed through corrections. One accounts for the motion of the satellite, the effect of special relativity, and the other accounts for the gravitational field of the Earth, the effect of general relativity. The values of the coefficients are very small, on the order of 1 billionth of a relative quantity, but they play a crucial role in the proper functioning of GPS. If they are not included, the system will lose accuracy in just a few minutes. An extra microsecond can lead to a loss of accuracy of 300 meters. By successfully using GPS, that is, by building correct routes with its help, we constantly confirm the validity of the theory of relativity, even without realizing it. The verification of new theories and the development of the theory of relativity did not put an end to the research of physicists on spacetime and gravity. After the publication of Einstein's works, many scientists proposed various ideas that became the basis for research beyond the theory of relativity. Hypotheses about the existence of new dimensions and different geometries emerged. Their names sound exotic: string theory, brane theory, and quantum gravity. While many of them are still in the formative stage, some clarifying, refuting, or expanding the theory of relativity may be tested in the coming years. At present, Einstein's theory seems quite robust. 3 classical experiments have proven that it best describes gravity in the solar system, and none of the modern experiments has been able to refute or challenge it. Nevertheless, in the relatively weak gravitational field of the solar outskirts, it is still difficult to separate conclusions drawn from the theory of relativity from those in other theories. To confirm the validity of a particular hypothesis, it must be tested under special conditions. For example, in the powerful gravitational field of a binary pulsar, or by investigating the propagation of gravitational waves. So far, research results confirm the theory of relativity, but scientists have not said the last word in the debate about the nature of the universe. Once merely a form of mythology, after Newton's discoveries, cosmology began to take on a more scientific character. However, it was only Einstein's theory of relativity that granted cosmology the status of a branch of physics. Humanity has long pondered the nature of celestial phenomena and their causes. From this perspective, cosmology, the science of the structure of the universe, is indeed as old as time. However, between its inception in ancient times and what we have today, this science has undergone a significant transformation. From a collection of myths, it has evolved into a field of scientific knowledge with a developed mathematical apparatus. The first changes in cosmology were brought about by Newton's discoveries in the late 17th century, and its reformatting was completed in the 20th century with the theory of relativity. Almost all ancient civilizations, at various stages of development, went through a period of creating myths explaining the creation of the world. These myths were passed down orally from generation to generation. This collection of beliefs was termed cosmogony, derived from the Greek roots cosmos, world, and gon, to generate. It must be acknowledged that it represented a bizarre mixture of life skills and myths about the supernatural and divine. Only during ancient Greece did the first precursors of future theories about the structure of the universe and the beginnings of modern cosmology emerge. Several centuries before our era, some philosophers began to ponder the causes of celestial phenomena, seeking to uncover patterns and harmony within them. For example, Pythagoras, circa 580 to 495 BC, and his followers claim that the world is governed by numbers, as evidenced, in their view, by natural rhythms and correct proportions. In other words, the Pythagoreans believed that mathematics rules the universe. About a century later, the great philosopher Plato, circa 400 to 348 BC, was the first to introduce the concept of cosmos. It encompassed harmony, order, and even beauty. Incidentally, the word cosmetics has the same origin from cosmos. Assuming that the cosmos is organized harmoniously, Plato proposed the idea that geometry could be the key to the laws governing the universe. The hypothesis of a geometrically correct world system anticipated modern scientific methods that view nature from mathematical and geometric perspectives. The best example of such an approach is the creation of the general theory of relativity. Almost 25 centuries after Plato's era, Albert Einstein's theory confirmed the ancient hypothesis and led to the establishment of modern cosmology. We can say that Plato was ahead of his time. Plato's universe was geocentric, meaning that the Earth was at its center and had a strict hierarchy. It was based on the highly harmonious structure of the sphere. The celestial bodies visible to the human eye, planets and stars, according to Plato, were located within concentric spherical layers, nested within one another and rotating relative to each other, thus moving both stars and planets. Aristotle, 384–322 BC, a student and associate of Plato, adopted the hypothesis of a geocentric hierarchical cosmos. He introduced a strict division of the world into the earthly and the celestial. The sublunar world extended to the orbit of the moon. In this world, everything was in constant change. Living beings, as well as inanimate matter, were born, grew, decayed, and died. Everything that existed in this world consisted of 4 basic elements in different proportions: earth, water, air, and fire. The celestial, or supralunar world included the heavens and stars. There, everything was the opposite. It was eternal and unchanging. The superlunar world was filled with a substance entirely different from the four earthly elements. According to the philosopher, it was a transparent, crystal-like substance from which the celestial spheres were made. Stars hung on them, and all movements naturally fit within these spheres. The world, according to Aristotle, was enclosed within the last sphere of the material world to which the stars were attached. A mysterious first mover was responsible for all celestial movements. In principle, the conveniently arranged universe of Plato and Aristotle's concepts reigned in minds for a long time, remaining the dominant theories of the structure of the universe until the 17th century. Many astronomers and mathematicians, such as Eudoxus of Cnidus, circa 400 to 355 BC, Callippus, circa 300 to 300 BC, or Ptolemy, circa 90 to 168 AD, tried to improve them while maintaining the basic principles, usually the spherical structure of the world. This structure, in various forms, survived antiquity, the Middle Ages, and the Renaissance, an astonishing resilience. However, over time, geocentric models came under increasingly open criticism from various scholars, Arab astronomers and mathematicians, Christian thinkers, notable scientists such as Nicholas Copernicus, Giordano Bruno, Tycho Brahe, Johannes Kepler, Galileo Galilei, and René Descartes, and these are just the most famous among many, initiated a great debate. Only in the 17th century did new concepts of world order finally take shape. Their essence was articulated in 1687 in Newton's Philosophia Naturalis Principia Mathematica, the great predecessor of Einstein. In the Principia, Newton derived the laws governing the motion of solid bodies, that is, their dynamics, and formulated the law of universal gravitation. This law confirmed the elliptical trajectories of the planets of the solar system, previously identified by Kepler. Overall, it is the force of universal gravitation that determines the entire range of motion of celestial bodies. Newton's main contribution was the introduction of the concept of the geometry of infinite and eternal space, serving as the framework for physical processes. In this simplest space, where Euclidean geometry operates, all fundamental processes of the universe occur. It has a rigid structure with no curvature. Mathematicians refer to it as flat, and it is unchanging. The phenomena occurring within it have no effect on it. For the first time in the history of science, physicists had a unified picture of the world. By that time, astronomers had already discovered that all stars, except for the Sun, were located at vast distances from the Earth, although measuring that distance was not yet possible. The closed world of Plato and Aristotle disappeared, replaced by a cosmos whose boundaries faded into infinity. Newtonian physics successfully passed all forms of experimental verification until the end of the 19th century. It explained the shapes of planetary orbits, the motion of comets, and enabled Urbain Le Verrier to discover Neptune. Newton's theory laid the foundation for modern physics. Moreover, it allowed cosmology to become a scientific discipline, as physics finally acquired a universal character. However, until the early 20th century, cosmology remained a rather modest branch of science, as it lacked high-precision observations of distant objects in the universe. It also lacked a unified concept of universal foundations that would connect all utilized concepts into a whole. It was Einstein's theory that shaped it. In 1915, the general theory of relativity completely changed the perception of universal gravitation. Gravity ceased to be a force of attraction. As noted earlier, Newton's Euclidean space lost its relevance. In a sense, it merged with time and the place of action, and physicists began to speak of space-time, deformed by gravity. This conceptual revolution turned cosmology upside down because, on the scale of the universe, gravity is the main type of interaction, and all other types, such as electromagnetic and nuclear forces, can be neglected. No one would even think to measure the level of electromagnetic interaction between galaxies. In 1917, Einstein proposed the first model of relativistic cosmology. The solution to the equations of his theory in the form of spacetime, possessing global geometric properties, was extended to the entire universe. Einstein based his model on three conditions. The first condition: matter is distributed uniformly throughout the universe. Most cosmological models subsequently retain this condition, which is known as the cosmological principle. Of course, this does not refer to absolute homogeneity. The condition holds only on gigantic scales, much larger than the sizes of galaxies. However, cosmologists, in the first approximation, are not interested in local properties, such as the change in space-time curvature caused by massive objects filling the universe, planets, stars, galaxies. They disregard these minor deformations, much like a geographer who considers the Earth a sphere while ignoring the details of its actual shape: mountains, valleys, and oceanic depressions. Global curvatures of the universe are the subject of study in relativistic cosmology. It is not a priori, non-zero, or variable. The second condition: the universe is closed, finite, meaning its expansion and volume are not infinite. This follows from Mach's principle. Among numerous critics of Newtonian views on absolute spacetime, Austrian philosopher and physicist Ernst Mach, 18th–19th centuries, stood out. His conclusions were exceptionally convincing. Quite possibly, due to his dual specialization, Mach believed that the concept of absolute space makes no sense, leading to the conclusion that it is impossible to determine any absolutely uniform acceleration or rotation. Imagine that an astronaut is flying in space and wonders whether he is rotating around his axis or not. Mach's interpretation suggests that rotation can only be noticed relative to other objects, stars, galaxies present in the universe. If the astronaut were in completely empty space, devoid of matter and energy, his question would lose all meaning. However, if he is indeed rotating around his axis, the astronaut should feel a centrifugal force pulling his arms outward. According to Newtonian logic, this centrifugal force is one of the manifestations of inertial forces arising from motion relative to absolute space. However, according to Mach's ideas, such a space does not exist, so the centrifugal force should be attributed to the influence of the total mass contained in the universe. Einstein utilized a significant portion of these assumptions, calling them Mach's principle. He laid them as the foundation for the development of the general theory of relativity and relativistic cosmology. In his view, space, or rather space-time, cannot possess the property of absolute existence, that is, exist independently of its material and energetic content. He stated, if everything in the world disappeared, then, according to Newton, the inertial space of Galileo would remain, while according to my view, nothing would remain. However, despite these statements, in his theories, Einstein did not strictly adhere to Mach's principle. The equations of general relativity still allow for the existence of a universe without any content in the form of spacetime with rudimentary geometry. Nevertheless, the theories of relativity resonate with Mach's ideas in many respects. Spacetime has a relative nature, as it depends on the masses and energies contained in the universe. It was Mach's principle that suggested to Einstein the idea of the finiteness of the universe, and that its volume is finite. If one accepts that inertial forces owe their existence to the total mass contained in the universe, it becomes difficult to imagine how this influence could be the result of matter scattered in an infinite continuum. However, if one accepts the finiteness of the universe, such a question does not arise. The assertion that the universe is finite does not imply that it has boundaries or walls. A cosmic traveler attempting to cross the universe, as described by Einstein's theory, moving in a straight line, would not encounter any boundaries along the way. On the contrary, he would return to his starting point, having made a circumnavigation of the universe. Of course, this journey can only be imaginary, as it would take billions of years. Just as an earthly traveler who moves in a straight line, regardless of obstacles, ultimately ends up back where he started after a circumnavigation of the Earth. Spheres with surfaces that have finite sizes but no boundaries. The third condition proposed by Einstein for his model: the universe is static, meaning it neither contracts nor expands and remains unchanged. In 1917, Einstein could not yet imagine that the universe could be expanding, as the results of relevant observations were not yet known. However, he already had grounds for some concern. The equations of the theory of relativity poorly aligned with the idea of a static universe. Einstein decided to slightly adjust the theory by introducing an additional factor that he called the cosmological constant. In the adjusted version, the universe could remain in place. The new constant, which fit well into the system of equations and played an important role in modern cosmology, allowed Einstein to complete the relativistic cosmological model according to his views. Today, it is known as Einstein's model. However, it was soon abandoned after the discovery of the expansion phenomenon, although it had already fundamentally changed the understanding of the universe. The cosmos became something unformed, nebulous, and suddenly transformed into a concrete physical object. It was Einstein's theory that allowed for the identification of spacetime as a flexible framework filled with matter and radiation, possessing a specific geometric form. From then on, this form became the object of cosmological study. Mathematically, it is expressed in terms of the curvature of a given system of equations and a typology that shows how individual points in spacetime are connected in complex or simple ways. A few years after the creation of Einstein's model, the quantity characterizing the geometry of spacetime was measured and easily related to the geometry of the expansion speed of the universe, or the Hubble constant. The fact that some of the most important characteristics of the universe could be physically measured, primarily the Hubble constant, as well as several other important parameters, conferred upon cosmology the status of a serious science based on observations. 10 years after Einstein created his model of the universe, Belgian physicist and canon Georges Lemaître found other solutions to the equations of the theory of relativity, in which the universe appeared to be expanding. His work laid the foundation for modern cosmology. But even before his emergence on the world scientific stage, Two discoveries made by astronomers during observations of the cosmos turned upside down both the theory of relativity and all conceptions of the universe, paving the way for new cosmological models. These were measurements of distances to other galaxies and the discovery that the universe is indeed expanding. Neither astrophysics nor cosmology can exist without defining the specific position and distribution characteristics of stars in the cosmos surrounding us. In the 18th century, technological progress allowed for the creation of sufficiently powerful telescopes through which astronomers Charles Messier, 1730 to 1817, and William Herschel, 1820 to 1822, discovered and catalogued a whole series of nebulae. These amazing cosmic objects, resembling a scattered cloud, are neither planets nor stars. John Herschel, 1801 to 1871, the son of William, published a general catalogue of nebulae and star clusters in 1864, indicating the coordinates of 5,000 cosmic objects. Some of them had a spiral structure, making them even more mysterious. Were these clusters of stars located at vast distances, similar to our own galaxy? Astronomer Thomas Wright, 1711 to 1786, and philosopher Immanuel Kant, 1724 to 1784, had already predicted the existence of such objects. The latter even poetically referred to them as islands of the universe. American astronomer Heber Curtis, 1872 to 1942, picked up this idea and articulated it more clearly. In 1914, it was believed that spiral nebulae could very well represent galaxies located at unimaginable distances, transforming them into tiny glowing spots for the human eye. During the same decade of the 20th century, astronomers began to raise important questions about our own galaxy. What is its structure, size? What is its place in the surrounding cosmos? What is the position of the Sun relative to other celestial bodies? These questions sparked extensive discussions that ultimately did not lead scientists to a consensus. It was only the American Edwin Hubble, who lived from 1913 to 1953, who managed to resolve the arising contradictions in the 1920s after many twists and turns. He worked at the Mount Wilson Observatory near San Francisco when a large telescope with a diameter of 2.5 meters was installed there. The power of the telescope allowed Hubble to understand that spiral nebulae indeed consist of stars. The astronomer observed them night after night and discovered stars of a special type within some nebulae, which were named Cepheids. These stars possess a very appealing property for researchers. Their luminosity varies periodically, and the period is quite accurately tied to the maximum brightness. If the period of luminosity change of a Cepheid is measured, meaning the time it takes for it to become less bright and then return to its maximum, this allows for the calculation of its intrinsic brightness, or the total amount of light energy it emits. On the other hand, from Earth, one can also observe the apparent brightness of the same star. The latter value depends both on its intrinsic brightness and on the distance to the light source. Finally, the results of simultaneous observations of the apparent brightness of Cepheids of the second and third periods, which allow for the determination of intrinsic brightness, enable the calculation of the distance to them and, accordingly, to the nebula they belong to. Using this clever method, which is indirect but highly effective, Edwin Hubble determined in 1924 the distance to the brightest of the spiral nebulae, visible to the naked eye in clear weather, the Andromeda Nebula, catalogued as M31 in Charles Messier's catalog, and calculated an incredible value of 1 million light-years. Today, this value has been increased to 2.5 million light-years. The nebula turned out to be located at a very significant distance from our galaxy. The hypothesis of island universes was confirmed in the most brilliant way. Spiral nebulae truly turned out to be other galaxies, distant star systems of impressive size. The universe suddenly expanded to volumes that are difficult to imagine, filled with gas and molecules in the form of galaxies similar to ours, separated by dizzying spaces. Hubble did not stop at this fundamental discovery and played an important role in the creation of the theory of the expanding universe. The American astronomer Vesto Melvin Slipher, who lived from 1930 to 1969, was the first to discover the phenomenon of the rapid movement of spiral nebulae even before Hubble uncovered their galactic nature. In the early 20th century, Slipher worked at the Lowell Observatory in Arizona. He measured the rotational speeds of nebulae and, using the newly developed technique of spectroscopy, which allowed for the visualization of the light spectrum emitted by a star, meaning breaking it down into a sum of emissions of different wavelengths. For example, a glass prism refracts white sunlight and allows one to observe its colorful spectrum. Each color corresponds to a component of a specific wavelength. Blue corresponds to the shortest waves, and red to the longest. A rainbow occurs when light is refracted in water droplets during rain. Each droplet acts as a tiny prism. We are accustomed to the concept of wavelength. However, it should be remembered that light represents a wave that propagates. Thus, it can also be characterized by the period of emission, which equals its wavelength when propagating near the observer. However, we have already noted that if the light source moves relative to the observed period of emission or wavelength differs from the emitted period. The deviation is usually slight and is measured as a spectral shift denoted by Z. If it has a positive value, the observed period or wavelength is longer than the emitted one. In this case, we speak of redshift, as the red part of the spectrum corresponds to longer wavelengths. Conversely, if Z has a negative value, we observe a blue shift towards shorter waves. These terms are traditionally used for the invisible part of the spectrum, such as radio waves and ultraviolet radiation. Measuring the spectral shift of a light source allows for the calculation of its speed relative to the observer, at least the radial component of that speed in the direction of the observer. It has a positive value if the source is moving away and negative if it is approaching. This phenomenon is called the Doppler effect. This effect has the same nature as the Doppler effect in sound waves, which we encounter daily. For example, the siren of an ambulance appears to us to be higher in pitch when it is moving towards us, because the length of the sound wave we perceive is shorter than the length of the emitted sound wave and lower when it moves away. Returning to Vesto Slipher, who tried to measure the rotational speed of the spiral nebula using the Doppler effect, he examined different regions of the nebula, which he believed should be rotating at different speeds. However, the measurement results were completely unexpected. Almost all nebulae showed red spectral shifts and appeared to be moving away from us at a considerable speed of several hundred kilometers per second. The research results were reported by the physicist at a meeting of fellow astronomers in 1914, causing surprise and excitement. However, Einstein learned about them much later. Slipher drew two revolutionary conclusions from his observations. On one hand, nebulae moving away at such high speeds cannot be located in our galaxy. He anticipated the conclusion that Hubble confirmed 10 years later, showing that these were other spiral galaxies. On the other hand, the speeds involved and the apparent prevalence of the phenomenon indicated that scientists had discovered a sort of universal motion, which he called expansion. Despite the lack of a theoretical foundation for these conclusions at that time, in the years following this astonishing discovery, astronomers accumulated results of redshift measurements, with its magnitude becoming increasingly significant. It became evident that scientists were dealing with a global phenomenon of cosmic scale. In 1922, British physicist Arthur Eddington, who lived from 1882 to 1944, called it one of the most mysterious puzzles of cosmology, and Hubble astonished everyone again in 1929. Based on the distance and speed measurements he obtained, he derived an empirical law that made him famous and bore his name. Although Georges Lemaître had already discovered it 2 years prior to Hubble, the speed of a galaxy's recession is proportional to its distance with a constant of proportionality, denoted as h, known as Hubble's constant. But how to understand this general divergence of galaxies? Cosmological models of the 20s of the 20th century were mainly reduced to Einstein's models and those of another scientist, Dutch astronomer Willem de Sitter, who lived from 1901 to 1934. Neither of them was suitable for explaining the phenomenon of redshift. Einstein's model was static, while de Sitter's model was designed for an empty universe without matter, which does not exist in reality. Concurrently with the astronomers proposing the idea of an expanding universe, Belgian physicist Georges Lemaître proposed a fundamental hypothesis arising from Einstein's relativistic equations. The universe continues to evolve. This idea led to the creation of the Big Bang theory and laid the foundation for modern cosmology. Georges Lemaître, the creator of the results of Vesto-Slipher's observations and the discovery of Hubble's law, placed cosmology in a very delicate position. Scientists agreed that the universe is expanding, but they could not find an explanation for this phenomenon. However, the gloom in the scientific community did not last long. Belgian physicist Georges Lemaître, who lived from 1906 to 1966, announced his discovery. He studied the materials from a symposium in Cambridge and wrote to his professor, Arthur Eddington, stating that he had found a solution to the problem that had troubled everyone for 3 years. It turned out that Lemaître had actually published it back in 1920. Unfortunately, it was in a very low circulation scientific publication. In new formulations of the equations of general relativity describing an expanding universe, in an article titled Homogeneous Universe of Constant Mass and Increasing Radius, he showed that his revised equations perfectly describe the phenomenon of redshift discovered by Slipher. They also implied Hubble's law, which would only be formulated 2 years later. Another physicist, Soviet scientist Alexander Friedmann, who lived from 1925 to 1922, simultaneously with Lemaître, formulated new equations of general relativity between 1922 and 1924. However, Friedmann derived them purely mathematically, without using them to describe specific processes in the universe. Among the solutions of this system of equations, known as the Friedmann-Lemaître metric, were both Einstein's static universe and de Sitters universe without matter. Now, they were merely special cases. However, the new equations described an expanding universe, and their solutions perfectly match the observational results. Eddington, understanding the significance of Lemaître's work, translated it into English in 1931 and tried to disseminate it as widely as possible. However, history was cruel to the scientist. The paragraphs of the article dedicated to the relationship between the speed of galaxies and their distance, that very constant, were not translated. This may explain why Lemaître did not become as famous as Hubble. Nevertheless, the scientific community reacted with enthusiasm to the results of theoretical research and acknowledged the fact that they matched observational results perfectly. Lemaître had to engage in several discussions, particularly regarding the cosmological constant, but soon his interest in it waned. He became fascinated with quantum mechanics, which was in the early stages of its development. Like most scientists of that time, he contemplated the possibilities and consequences of the advancement of this field of science. This topic sparked fierce debates in which Einstein did not actively participate, taking a position that still provokes controversy today. The merit of Georges Lemaître lies in his ability to connect general relativity and observational results into a cohesive whole, thereby creating the foundation of modern cosmology. However, how should we understand the concept of an expanding universe? General relativity gives this term a special meaning. It refers to the expansion of space, but this is not the kind of expansion where any boundaries shift or space occupies more room. In reality, there is nothing that can be considered external to space, and the latter increases without disturbing anything that might be outside. Imagination and intuition do not assist us in this situation. Fortunately, there is mathematics, and non-Euclidean geometry handles the description of this phenomenon exceptionally well. It interprets expansion as a special property of the curvature of spacetime. Let us try to clarify the terminology. Familiar vocabulary suggests the expansion of the universe as something akin to an increase in space over time. In this case, the very concepts of space and time do not have a clear definition, or rather, they have none at all in the theory of relativity. Thus, these terms should not be taken literally in a colloquial sense. They serve more for an intuitive description of a process that actually has quite clear characteristics. In the process of expansion, galaxies remain tied to space. They are stationary relative to it, but they are carried along by the expansion of space, and the mutual distance between celestial bodies is constantly increasing. What can this be compared to? Galaxies resemble raisins in baking bread, or stars drawn on the surface of an inflating balloon. Of course, all these analogies are misleading, as the expansion does not occur in some other medium that would be external to space. In reality, galaxies are not rigidly tied to a specific location. A particular galaxy, attracted by neighbors or a cluster of galaxies, begins its own separate motion, which overlaps with the expansion process, complicating cosmological analysis. The distance separating two galaxies being drawn apart by the expansion process is constantly increasing, and our own galaxy is naturally subject to this phenomenon as well. All other galaxies are receding from us, all at an equal rate, and the distance is increasing ever more rapidly as they move away. This increase represents the speed of expansion, which underlies the spectral shifts. It should be remembered that cosmic expansion has no center. Of course, all galaxies are moving away from ours, but they are doing so just like any other randomly chosen galaxy. This is further proof that visually representing this expansion is practically impossible. Hubble's law states that the observed speed of galaxies receding is equal to the distance to our galaxy multiplied by a proportionality constant. The current expansion coefficient of the universe is known as Hubble's constant. Georges Lemaître and Edwin Hubble provided estimates of this constant in their articles. However, it later turned out that its value is nearly 10 times greater. It took astronomers almost a century, using increasingly powerful and sophisticated telescopes, to obtain the value of H0 with an accuracy of a few percent. Recent measurements conducted using orbital telescopes have determined the value of H0 to be approximately 67 kilometers per second per megaparsec. A megaparsec is a distance in space, about 3.26 light years. 1 megaparsec equals 1 million parsecs. This means that a galaxy located 1 million parsecs from ours, 3.26 million light years away, is receding due to the expansion at a speed of 67 kilometers per second. A galaxy that is 10 million parsecs away from us is receding 10 times faster, that is, at a speed of 670 kilometers per second, and so on. However, the law complicates for very large distances. In the early 1930s, after the creation of new equations of relativity theory, Georges Lemaître continued his work in cosmology. He understood that the expansion of the universe implies a decrease in the density and temperature of its contents. It turned out that in the distant past, the contents were denser and hotter, meaning that if one were to reverse time, one could see galaxies converging towards each other until they completely merged, merging first into molecules and then into atoms. The density of matter in the universe would have been the same as in an atomic nucleus. Lemaître proposed that the modern universe resulted from the expansion and dilution of some initial, very dense state, which he called the primeval atom. He also named his model of the origin of the universe the same. The theory of the primeval atom became a precursor to the Big Bang theory. The foundation of the theory was the idea of the existence of a very dense and very hot core, the density and temperature of which exceeded all known values today, and in which corresponding physical processes occurred. The name Big Bang appeared later. In 1949, British astrophysicist Fred Hoyle, who lived from 1915 to 1981, jokingly ridiculed the idea of the primeval atom during a radio broadcast. He himself adhered to opposing views and advocated a competing idea of a static universe. However, the name appealed to the general public, and since then, Lemaître's idea received a new name. The main idea of the Big Bang theory is simple. If matter is immutable and does not spontaneously arise or disappear in the universe, then its initial quantity spreads in an ever-increasing volume as a result of expansion and dispersion. According to known physical laws, this dispersion of matter is accompanied by increasing cooling. The density and temperature of the medium in the universe continue to decrease, and it has not always looked as it does today. The universe has a history. It has undergone a genuine evolution. Nowadays, this has become evident, but the scientific community long resisted the idea of the primeval atom. Einstein also did not like the concept of the primeval atom from which the history of the universe supposedly began. He thought that it resembled too closely a divine idea of creation. Although Lemaître, let us remember, a priest, always emphasized, and justifiably so, that his theories did not imply any creation. These foundational theories clearly defined the development program of cosmology from the 30s of the 20th century. The primary task of science became the detailed study of the history of the universe, starting from the period of maximum density to today's galaxies. Astrophysicists Fred Hoyle, Thomas Gold, who lived from 1920 to 1984, and Hermann Bondi, who lived from 1919 to 1955, proposed alternative solutions. In 1948, in two articles, one written by Bondi and Gold, the other by Hoyle, they described their a priori paradoxical model of an expanding universe viewed as static. This model was based on the universalization of the cosmological principle recognized by all, which states that if the universe is viewed on a sufficiently large scale, it will be found to possess the same properties in all directions, regardless of where the observer is located. The refined cosmological principle proposed by Bondi, Gold, and Michael went even further. It was added that moving observers would not be able to detect any changes in the global characteristics of the universe. It would remain essentially the same at any moment in its evolution. In other words, in this model, the universe has no history. It is always unchanged, ageless. The idea was, of course, quite seductive, as it revived the myth of an eternal and unchanging universe. However, it seems that it was initially incorrect and had no chance of winning in the competition with the idea of an expanding universe, which spread first in the 1930s. Astronomers saw it with their own eyes. Expansion implies dispersion and cooling of matter, meaning change is continuous and inevitable. How could one promote a theory that contradicts observations? Nevertheless, Bondi, Gold, and Hoyle offered quite original explanations for the observed phenomena, constancy, and the creation of new matter. If matter is constantly formed in proportions that compensate for the dispersion caused by expansion, the density remains unchanged, and the universe retains its previous global properties. According to the hypothesis, new galaxies gradually formed from this newly created matter. Bondi and Gold's calculations showed that to maintain a constant density of matter in the universe, it would be sufficient for one atom to arise per cubic meter every billion years. Such reasonable creations did not seem so absurd. In any case, the theory of the stationary universe enjoyed some recognition for a time. Moreover, the Big Bang model was facing significant difficulties at that time due to issues with determining the age of the universe. However, this theory ultimately could not establish itself. More accurate astronomical observations increasingly clearly indicated that the universe indeed evolves. In the 1950s, research on radio signals conducted by British radio astronomer Martin Ryle, who lived from 1920 to 1984, and was awarded the Nobel Prize in Physics in 1974, completely disproved the idea of a static universe. Additionally, new arguments in favor of the Big Bang emerged from nuclear physics, which was just beginning to develop rapidly. Hoyle had to admit, in 1964, that stationary models seemed unable to explain the abundance of helium atoms in the universe. While this was entirely natural for the process of primordial nucleosynthesis predicted by the Big Bang theory. Finally, a year later, stationary universe models were permanently discarded after the discovery of cosmic background radiation. Following Georges Lemaître's reasoning, in the very distant past, all cosmic dimensions must have been extremely tiny, and the density and temperature enormous. To such an extent that at some point the distances between individual components were practically equal to zero, while the density and temperature approached infinity. It is this extreme state that was called the Big Bang, as it creates an impression. However, it is completely misleading to think that the universe suddenly emerged, exploding. The deeper we delve into the past, the more the properties of this primordial universe, its highest density and temperature, suggest the existence of phenomena very far removed from those described in classical physics. At a certain moment in the past, physical laws lose their ability to explain the processes occurring. Special conditions predetermine the existence of quantum interactions. As Georges Lemaître predicted, modern science is capable of adequately describing processes occurring at the level of atoms and microparticles, but it cannot describe phenomena that unfolded against the backdrop of the intense gravity that prevailed in the universe due to the extremely high concentration of matter. Modern physical laws are inapplicable to those special conditions. The earliest stage of the universe's formation that can be theoretically explained is called the Planck epoch, named after German physicist Max Planck, who lived from 1806 to 1914, the founder of quantum physics, who initiated the second scientific revolution of the 20th century immediately following the upheaval brought about by general relativity. The state of the universe before the Planck epoch remains unknown, as it does not lend itself to modern theoretical explanations. As for quantum physics, in the 30s of the 20th century, it became the most popular topic of scientific discussions, somewhat sidelining cosmology. Einstein also became fascinated by it. Models of the Big Bang show that a temporal interval separates us from the Planck epoch. Thus, we know very little about this period of the universe's development, but it is quite clear that it was unlike anything else, truly special. The universe began to exist in its modern form only after its conclusion, so its age is considered equal to this interval. Most models suggest that the value of Tu should be of the same order as the value of Th, the reciprocal of Hubble's constant, that is, just over 10 billion years. Data on the composition of the universe and the geometry of spacetime collected during astronomical observations indicate that the value of Tu is approximately 13.8 billion years. But note, this does not mean that the universe emerged 13.8 billion years ago. In reality, we do not know what happened in the pre-Planck epoch and how long it lasted. Today, scientists can determine the age of some objects in the universe using various methods. The age of the oldest stars and star clusters is estimated by astronomers to be 12 billion years, which is quite close to Ta. This result is crucial, as the Big Bang theory is currently the only way to explain why the age of celestial bodies has a limit. So far, no hypothesis has been proposed that could explain this phenomenon by other means. Therefore, the age of the universe is of great significance for confirming the validity of the Big Bang theory. Fleeting contradictions. The central idea of Georges Lemaître's theory, which suggests that the universe has changed incredibly since its youth, did not immediately win over the scientific community. Initially, physicists rejected it, or, at best, accepted it coolly. Many of them were interested in the new direction of science, quantum physics. As mentioned earlier, Even Einstein did not enthusiastically embrace the concept of the primeval atom, as it resembled the creation of the world. Moreover, the very idea of concentrating the universe in a single point of infinite density seemed absurd to him from a physical standpoint. Lemaître's theory did not gain recognition also because it appeared to contradict all known facts. If scientists relied on its calculations, measuring cosmic expansion in 1929 would have led to an estimate of the universe's age of less than 2 billion years. However, at that time, geophysicists estimated the age of the Earth to be 6 billion years. Today, this figure has been adjusted to 4.54 billion years, while stars are estimated to be as much as 1,000 billion years old. It turned out that the universe was filled with bodies much older than itself, and naturally, Lemaître's theory was ignored. This explains the fact that a significant portion of the scientific community leaned towards the competing theory of a stationary universe. It seems that Einstein also leaned towards this hypothesis starting in 1931. However, he quickly dismissed it, not publishing a word on the matter. Despite this evident setback, Lemaître and some other proponents of the Big Bang continued to believe that this hypothesis was correct. Moreover, who could confirm that the measurements of 1929 were performed correctly and that Lemaître was indeed right? After all, later, in 1952, the first estimates of the universe's age turned out to be completely erroneous again. When the error was corrected, it was found that the universe is around 14 billion years old. The Big Bang theory, once again, became not only acceptable, but also extremely convenient, as the age of the cosmos coincided with the age of the oldest stars. Models of a static universe and other alternatives to the Big Bang theory proved incapable of explaining such a result. In the 30s of the 20th century, nuclear physics, which focused on the structure of atoms and nuclear reactions, was a very young field of knowledge and was actively developing. One of its founders, American physicist of Russian descent, George Gamow, who lived from 1904 to 1968, was surprised to discover that various atoms existing on Earth are distributed in roughly the same proportions throughout the universe. He initially suggested that all chemical elements arose from nuclear reactions within stars and then spread everywhere. However, in the 1940s, Gamow realized that this could not have been the case for all elements and modified his hypothesis. Utilizing Lemaître's theory, he, along with colleagues Ralph Alpher and Robert Herman, established that some elements could have originated earlier in the primordial stage of the universe's development. In fact, the extreme densities and temperatures accompanying the birth of the universe represented ideal conditions for initiating nuclear reactions. Gamow called this primordial soup, or, using the ancient Greek term for primordial matter, the primeval soup of condensed matter that filled the universe at that time. He simply recalled the name invented by Aristotle for the fundamental substance from which all matter formed. In any case, the idea revived the scientific community's interest in cosmology. The article outlining the foundations of primordial nucleosynthesis, the synthesis of atoms in the young universe, was published on April 1st, 1948. Gamow had a very vivid sense of humor and titled the article Alpha Beta Gamma after the first letters of the author's surnames, Ralph Alpher, and George Gamow. In reality, Beta did not participate in writing the article. However, Gamow added his surname to the list of authors specifically for the April Fool's joke. The hot universe model proposed by Gamow and his colleagues initially did not gain widespread recognition due to the overly contradictory estimates of the universe's age at that time. The stationary model was still more successful. However, new observational results changed the situation. Astronomers noticed that the proportional content of certain light elements, deuterium, helium, and lithium, has a universal and ubiquitous character, meaning that these atoms could not have been created in the cores of stars, but only in conditions of superdense and very hot substances described by the Big Bang theory. The predictions made using the theory match the observed results perfectly. Researchers concluded that other atomic nuclei formed in the cores of stars during stellar nucleosynthesis. However, the distribution of light atoms was sufficient to confirm the hypothesis of the Big Bang. The hypothesis of primordial nuclear synthesis has another equally important implication. If it indeed took place, as follows from the Big Bang theory, it leads to the conclusion that there exist no more than 4 families of elementary particles, corresponding to fairly simple criteria. This conclusion was of great significance for physics, as particle physicists at the time speculated the existence of around 100 different particles. To put it briefly, various families of particles were somewhat analogous to each other. Each consisted of the same number of particles, differing only in mass. For example, the electron, representing the first family, has a more massive counterpart called the muon in the second family, and an even more massive one known as the tau lepton in the third. In the ordinary matter, which makes up our bodies, planets, and stars, consists of particles from the first family, to which electrons belong. Particles from other families are unstable. In 1989, experiments conducted at the Large Electron-Positron Collider, a massive accelerator of the European Organization for Nuclear Research, CERN, located near Geneva, were able to confirm the hypothesis of primordial nucleosynthesis. The experiments ultimately demonstrated that there are only 3 families of elementary particles. This was an undeniable argument in favor of the Big Bang theory. The discovery of cosmic microwave background radiation in 1965 dealt a final blow to theories that denied. The Big Bang, the foundation of modern cosmology, was subsequently fully formulated. It is based on equations formulated by Alexander Friedmann and Georges Lemaître in the 1920s. However, several versions of the Big Bang have also been developed, as the parameters that could characterize it during the time of Gamow were still largely unknown. We know much more about them today, but still not everything. One of the main tasks for cosmologists was to determine which version most adequately describes the actual universe. Each version was characterized by its own formula for the evolution of a scaling factor that defines cosmic expansion. The current rate of evolution, the logarithmic derivative of the cosmic time function, is identified, for example, with the Hubble constant. After conducting dozens of measurements, the accuracy of which continually improved, and after heated debates, astronomers were able to estimate both this constant, approximately 67 kilometers per second per megaparsec, and the age of the universe, about 13.5 billion years. However, other parameters characterizing our cosmos still need to be measured and even simply understood. For instance, astronomers are quite reasonably convinced that in addition to ordinary matter, there is a large amount of invisible or dark matter in the universe. All this matter, both visible and invisible, should, according to Einstein's laws, exert gravitational attraction, which, in theory, should slow down the expansion of the universe. Gravity, as we know it, always acts as an attraction. Planets, stars, and galaxies attract other celestial bodies, but never repel them. However, measurements begun in the late 1990s show a directly opposite result. The expansion of the universe seems to be accelerating. Some astrophysicists, investigating the age of the universe and the processes of galaxy formation, suspected this acceleration. It was predicted by the cosmological constant introduced by Einstein in 1917. Georges Lemaître found this assumption particularly interesting. The constant symbolizes a repulsive gravitational effect that manifests only on the scale of the entire universe, and all observational results regarding the change in acceleration, for instance, perfectly align with Einstein's predictions. Lemaître suggested that the effect of the cosmological constant could be analogous to that of so-called vacuum energy. This idea was taken up by many researchers who believed that the acceleration could be caused by some substance of this type, called dark energy or strange energy. However, the nature of this hypothetical component remains unknown, and no theory even suggests what it could be. When Einstein developed his first cosmological model in 1917, there were no observational results confirming the phenomenon of the universe's expansion, and the scientist himself was unaware of it. However, his equations in their original form did not allow for the consideration of the universe as a static object, and Einstein modified them by introducing, in addition to Newton's gravitational constant, a second fundamental constant. It was named the cosmological constant because it pertained to the existence of the universe as a whole and allowed it to be considered static. According to observational data from that time, cosmic expansion was discovered in the 1920s. Einstein acknowledged his mistake. He considered it the greatest error of his life and removed the constant, deeming it unnecessary. However, Georges Lemaître continued to advocate for its necessity, as the existence of the constant allowed for reconciling the theoretical age of the universe, in reality erroneous, with the age of the Earth. Nevertheless, his viewpoint was not supported in Europe. Most colleagues believed that the constant was equal to zero, which allowed it to be dismissed as unnecessary. Decades later, observational results, particularly those concerning the ages of stars and the formation of galaxies, did sow doubts and partially rehabilitate the constant until, in the last decades of the 20th century, striking data regarding very distant supernova explosions were obtained. These data allowed for the suggestion that the expansion of the universe is accelerating. According to known laws of physics, matter and energy in the form of radiation can only slow down the expansion, meaning that the acceleration is caused by some other force. But what force? The cosmological constant aligns excellently with the observed acceleration of expansion. Nevertheless, despite this remarkable coincidence, some physicists refuse to acknowledge the existence of this constant. They prefer to allow for the existence of some exotic substance that could be attributed to the acceleration of expansion. They call it dark energy, quintessence, or vacuum energy accelerator. The choices are vast, although the hypothesis seems interesting a priori. However, what commonality could there be between particle physics and the acceleration of expansion? Even without special calculations, the natural order of magnitudes typical for particle physics would require a phenomenon of much greater power than what is observed in nature, approximately 1 with 120 zeros more powerful. It is hard to imagine a hypothesis that is so poorly aligned with reality. The most astonishing thing is that some scientists consider this discrepancy a problem of the cosmological constant, even though the problem arises only when we deny the existence of this constant. The relationship between particle physics and cosmology can sometimes become quite tense. Should science reintroduce the constant into the general theory of relativity? The arguments presented suggest that it should. In this case, the status of lambda to denote the constant in the equations of general relativity uses the Greek letter lambda, and it is sometimes referred to by that letter. The lambda term would then be analogous to the status of other physical constants. The value of lambda is not derived theoretically. It can only be measured. In this case, that is indeed what happens. It is constant and actually corresponds to cosmic acceleration and aligns with other estimates. But what does this mean from a physical standpoint? According to the theory of relativity, the content of the universe curves spacetime. This constant entails the presence of curvature even in absolutely empty spacetime devoid of matter. As early as the 1920s, Dutch astronomer Willem de Sitter proposed a model of spacetime that possessed a constant curvature not equal to zero. By inserting matter into such a universe, we obtain spacetime that is precisely like ours. Moreover, de Sitter's model aligns perfectly with the solution to Einstein's equations for the special case of spacetime without matter. The empty universe with a non-zero cosmological constant de Sitter considered a fundamental property of the universe. It can be interpreted as the curvature of a constant empty spacetime. The curvature of three-dimensional space, not to be confused with four-dimensional spacetime, although the separation of time and space in the theory of relativity is always artificial, represents another parameter that cosmologists would like to estimate with sufficient accuracy. Einstein created a model in which space had finite dimensions and positive curvature. However, any other solutions are also possible. Curvature depends on what is present in that space, as well as on the value of the aforementioned cosmological constant. Only measurements of the highest precision, for example, of the diffuse extragalactic background radiation, allow for its estimation. Current data indicate that the curvature of space is quite small. Some researchers believe it to be zero. They even speak of a flat universe. The discovery in the 1960s of radiation permeating the entire universe confirmed the correctness of the proponents of the Big Bang model. Its study led to very important conclusions. Significant discoveries were made at the most opportune moment. Initially, when George Gamow proposed his hot universe model in 1948, the hypothesis of primordial nucleosynthesis, that is, nuclear synthesis, encountered a number of difficulties. Observations showed that helium atoms constitute about 24% of the total mass of ordinary matter in the universe, while hydrogen atoms account for about 74%. All other elements make up the remaining 2%. However, according to initial calculations, primordial nucleosynthesis should have produced much more helium within the first few minutes. To explain this seemingly outrageous result, Alpher and Hermann, colleagues and students of Gamow, proposed a rather original solution. The primordial universe must have been filled with an enormous number of photons, particles that constitute light, more precisely, electromagnetic radiation. These photons slowed down the production of helium. But how? It should be clarified that during primordial nucleosynthesis, matter was sufficiently hot and dense, and light elements were created through a sequence of fusion processes. A proton and a neutron clinging to each other formed a deuterium nucleus, and another identical pair attached to it formed a helium nucleus. 2 protons plus 2 neutrons. Alpher and Hermann suggested that countless collisions of photons with deuterium nuclei could hinder their fusion, resulting in slightly less helium being produced than could have been. The researchers did not stop there in their reasoning. What happened to the disruptive photons when the density and temperature decreased and became insufficient for atomic nuclei to fuse? They could not just disappear, and must have continued to linger in space, even to this day. The expansion of the universe should have dissolved these photons in an ever-increasing volume. And that's not all. It should have increased the wavelength of each photon, gradually reducing the energy of the primordial radiation, since the energy of a photon is inversely proportional to its wavelength. Or, to put it another way, making it less and less hot, since the temperature of gas or radiation represents the average energy per particle. Alpher and Hermann calculated that by now, the radiation should have a wavelength too long to be seen with the naked eye. In 1964, this assumption was reformulated by several teams of scientists: Soviet physicists Andrei Doroshkevich and Igor Novikov, American physicists Robert Dicke and Jim Peebles. The American scientists hurried to conduct an experiment at Princeton University to detect ancient photons. Unfortunately, they were unexpectedly outpaced. Not far from Princeton, a telephone company investigating interference in satellite phone communication since the late 1950s, Arno Penzias and Robert Wilson, engineers of the company, created an antenna designed to detect weak signals emitted by satellites. In 1963, they decided to repurpose the antenna into a radio telescope to capture radio waves emitted by stars and galaxies. From the very beginning of their observations, Penzias and Wilson noted a persistent constant interference in all their results. No matter which direction they oriented the antenna, the received signal was always more intense than theoretically calculated. They checked the equipment several times, ran pigeons that had nested in the antenna through it, but nothing helped. The interference persisted stubbornly in all recordings. Finally, they realized, with the help of some colleagues, that they were on the brink of a great discovery. They officially announced their discovery in an article published in 1965. However, the explanation for the phenomenon was provided by scientists from Princeton. It was the very electromagnetic radiation that originated in the stage of the hot and dense young universe. The scientific community recognized the validity of the Big Bang theory, as it was the only one that could explain this, and its proponents had long sought this very evidence of such relic radiation. This discovery earned Penzias and Wilson the Nobel Prize in 1978. Observations by the scientists established that each liter of volume in the modern universe contains about 420,000 relic photons. This number may seem gigantic. However, for comparison, it can be noted that each liter of cosmic space in Earth's orbit on the daytime side of our planet contains about 4,000 billion photons emitted by the Sun. let us mentally return to the dense and hot phase of the universe's formation to understand the reasons for the emergence of relic radiation. At this stage of the universe's formation, all matter was ionized. What we today call atoms simply did not yet exist. That is, atomic nuclei, to which surrounding electrons, charged particles, are attached, were freely circulating. These included protons, the precursors of hydrogen nuclei, a certain number of ionized nuclei of future helium atoms, and free electrons. The medium was filled with energy, and collisions between extremely energetic photons and the remaining matter occurred infinitely. As soon as an electron joined any nucleus and formed a primordial atom, it was immediately attacked by a photon. In turn, photons constantly collided with not neutral, but electrically charged electrons and proton nuclei. These collisions changed their direction of motion and altered their energy. A process of diffusion, the scattering of photons, occurred, similar to what happens in fog when light reflects off rows of tiny water droplets. The result was analogous. Beams of light could not propagate freely. Nothing was visible. The medium was opaque, albeit filled with electromagnetic radiation. It is somewhat similar to what happens inside the sun. Thus, the primordial universe was completely opaque and possessed the properties of an absolute black body, and no observer could hope to see anything in it, no matter how much light was directed there or how hard they tried to catch an outgoing beam of light. However, as the universe expanded, processes of inflation and cooling took place. The decrease in density and temperature changed the situation. Collisions of photons with matter became increasingly rare. As their number decreased, protons were able to start forming stable bonds with electrons. The formation of the first hydrogen atoms began. This phase is called the recombination phase. It marked the end of the opaque black universe stage. Photons actively interacted with ionized electrically charged matter until the recombination of atoms, but they ceased to react with atoms due to their neutrality, lacking an electric charge. When the majority of matter presented itself in the form of neutral hydrogen atoms, relic photons could begin to move freely without collisions. At that moment, the universe became transparent. The recombination phase ended 380,000 years after the completion of primordial nucleosynthesis, just before 13 billion years ago. Matter began a long process of concentration under the influence of gravity. This phase was named gravitational instability, leading to the emergence of stars and galaxies. The primordial photons continued to propagate, encountering almost no obstacles along their way. They represent the very relic background radiation discovered by Penzias and Wilson. The relic radiation confirms the existence of that distant epoch when the universe was forming. It is a fossil legacy from youth. Its detailed study has allowed scientists to make numerous discoveries. At the time when the background radiation finally gained freedom, the universe was still a hot soup, in thermodynamic equilibrium at a very high temperature, like in an oven heated to the maximum. The laws of physics unequivocally state that radiation emitted by a hot object possesses one very significant property. Its color, more precisely, the distribution of wavelengths, known as the spectrum. And intensity depends solely on the temperature of the emitting object. Radiation always consists of photons with varying wavelengths. The spectrum shows the proportional relationship of photons and, consequently, the intensity of radiation concerning wavelength. If radiation is emitted under conditions of thermodynamic equilibrium, its spectrum has a very characteristic and well-known bell-shaped form, called the black-body spectrum. The maximum intensity is characteristic of wavelengths, that is, colors, depending solely on the temperature of the emitting object. We return to the same point. Each curve corresponds to a specific temperature of the emitting object. Maximum intensity is reached at a specific wavelength, that is, color, which depends only on that temperature. The higher the temperature, the shorter the wavelength located at the maximum of the curve. It is inversely proportional to temperature. The higher the temperature, the more noticeably the spectrum shifts towards shorter wavelengths, that is, towards waves with higher energy levels, from red to blue. For the case of visible light waves, during the recombination epoch, the temperature of the universe approached 3,000 kelvins. Kelvin is an absolute measure of temperature, unlike relative ones expressed in degrees. A value of 0 kelvins means absolute zero, which is minus 273.15 degrees Celsius, the lowest temperature that can be imagined, corresponding to a state that is, in reality, unattainable, where atoms become completely motionless. Above absolute zero, changes of 1 Kelvin correspond to 1 degree Celsius, that is, plus 273.15 kelvins equals 0 degrees Celsius. The relic background radiation formed at a temperature of 3,000 kelvins. This corresponds to a maximum intensity for a wavelength of about 1 micron, characteristic of visible red light. Gradually, the expansion of the universe cooled the radiation, increasing the wavelength of each photon. Today, it is approximately 1 millimeter, corresponding to the wavelength of micro-radio waves. Therefore, Americans and English refer to the radiation as cosmic microwave background. Its temperature has decreased to 2.735 kelvins. It took time to prove that the background relic radiation had a black body spectrum. Penzias and Wilson observed it already with a changed wavelength, insufficient to determine the original spectrum. Only some other measurements allowed for results that contributed to the formation of ideas about the primary spectral composition of the radiation. However, for a correct analysis of the entire spectrum, it was necessary to go beyond the Earth's atmosphere, which absorbs a significant portion of microwave radiation. To ultimately solve the problem, in 1988, NASA launched the COBE, Cosmic Background Explorer, satellite. By 1989, it showed that the data of the background radiation matched the theoretical calculations for a black body with astonishing accuracy. Its temperature was about 2.74 kelvins, regardless of the direction of observation. No further hypotheses were put forward by scientists. The confirmation of the theory was extremely convincing. From COBE to Planck, more and more details emerged. The American satellite WMAP also became a pioneer in observing microscopic anisotropies, temperature variations depending on the location of the measurement area in space. The measurement results were announced in 1992 and caused a sensation, earning George Smoot and John Mather, the project leaders, the Nobel Prize in Physics in 2006. However, the picture of cosmic radiation remained somewhat unclear, as the satellite could not reveal a picture with an accuracy greater than 7 degrees between observation directions. Obtaining precise cosmological results was challenging. In the following decade, several projects aimed at detailed studies of background radiation were launched. The Boomerang experiment utilized a telescope mounted on a balloon. In 1999, it measured the anisotropy of background radiation with a 1-degree step, albeit over a rather narrow section of the celestial sphere. The WMAP, Wilkinson Microwave Anisotropy Probe, sent by NASA into the stratosphere in 2001, was more successful. By 2003, it managed to create complete maps of the sky, with 5 different wavelengths measured at a step of only 20 angular minutes, 1/3 of a degree. Finally, scientists obtained a clear and precise picture of background radiation. The third satellite that conducted extensive studies of background relic radiation was named Planck, in honor of the great German physicist. The satellite was launched into space by the European Space Agency in May 2009 and was intended to obtain final clarifying results. In March 2013, it sent results back to Earth that were 3 times more accurate than those of its predecessor and across 9 different wavelengths. These clarifying data allowed for the correction of many cosmological parameters. For example, the age of the universe is now nearly 13.5 billion years, slightly older than previously thought. The value of the Hubble constant is approximately 67.8 kilometers per second per megaparsec. The analysis of the maps created by Planck is still ongoing, but in conjunction with the results from other experiments, it should provide us with additional knowledge. In particular, cosmologists and other physicists eagerly await data on gravitational waves that may have formed in the very early stages of the universe's history. Almost isotropic, but not entirely, the photons of the relic background radiation have interacted very little with matter since the onset of radiation, thus providing us with a picture of the state of the universe during the recombination epoch when stars and galaxies had not yet formed. The soup of matter and radiation was quite homogeneous. The theory posits that the relic radiation should be completely isotropic, meaning its temperature and spectrum should be the same across the entire celestial sphere. The data properties of the radiation have been tested with great precision, approximately to 1 part in 100,000%. This means that the physical conditions were the same in all directions of space during the recombination epoch. Once again, it turns out that only the Big Bang theory can explain the existence of such a level of homogeneity and isotropy. However, the homogeneity of relic radiation is not so easy to identify, even when observing it in space. First of all, it should be taken into account that everything is in motion. The Earth rotates around the Sun, which in turn moves relative to the center of the galaxy, and the galaxies themselves move in their own directions. As a result, a Doppler effect occurs, and the radiation shifts towards the blue part of the spectrum, in the higher energy region, in the direction of our movement, and towards the red in the lower energy region in the opposite direction. This effect, known as the dipole effect, has been measured quite accurately and received a clear explanation. It allows for the calculation of the speed at which we are moving through the universe. After measuring and discarding the motion component, there are still various external influences that need to be identified. Microwave emissions emitted by various celestial bodies overlap with the relic radiation and create interference for obtaining results. Astronomers have to identify and remove them with utmost care. This is not as simple as it seems, However, astronomers believe they have already managed to cope with the problems. This is very important because in reality, the Big Bang theory does not imply absolute homogeneity of the universe. The relic radiation may be nearly isotropic, but not entirely so. The universe could not have been perfectly homogeneous during the recombination epoch, and thus the relic background radiation also exhibited slight density fluctuations. In fact, if everything had been perfect, matter would never have been able to begin the condensation process due to that perfection. And it is precisely this process, influenced by changing gravity, that became the foundation for the gradual formation of galaxies and stars. For this process to initiate, it was absolutely necessary for small inhomogeneities to exist even at the stage of recombination. The theory, therefore, suggests that some regions of space may be warmer than others. This was confirmed by observations on the map of relic radiation, initially with data from the COBE satellite, and then with more precise data obtained from later projects. The temperature of relic radiation can vary between different areas of space by about 1/1000th of a degree. This anisotropy is observed in full accordance with the Big Bang theory, corresponding to both the value and statistical distribution. Another additional confirmation of the theory's correctness. It informs us that there were fluctuations in matter that laid the groundwork for cosmic structures in the future. Scrupulous studies of weak anisotropy have led to astonishing results. Its distribution revealed not only the existence of matter fluctuations during the recombination epoch, but also the global geometry of spacetime. The study of anisotropy has provided scientists with a new tool for measuring parameters of this geometry. In combination with other data, it has allowed for the precise determination of various characteristics of the universe as the propagation of light rays, cosmic optics, depends on the geometry of spacetime. Any distant object, as well as a particular region of relic radiation, can be distorted, enlarged, reduced, or amplified in accordance with curvature. The details of the anisotropy distribution show, for example, that our space has very little, almost zero curvature. This is referred to as a flat universe, although any curvature value would theoretically be possible. Observing the anisotropy of relic radiation tells researchers a lot about the composition of the universe, and its properties depend on the total amount and characteristics of both visible and invisible matter, as it is this matter that generates the curvature of spacetime geometry according to Einstein's equations. From this, for example, one can derive the average density of matter, both visible and invisible together, the density of the baryonic component, that is, ordinary matter, the existence of the cosmological constant. All of this aligns with the data provided by other observations. This has prompted cosmologists to refer to the Big Bang model as the concordance model. When dealing with a powerful gravitational field, original formulations of the theory of relativity become necessary. Its distinction from Newtonian physics becomes apparent. Some celestial bodies and astrophysical phenomena allow it to shine in all its glory. Very massive stars, those whose mass exceeds 8 times that of the Sun, end their lives quite violently. When they exhaust their nuclear fuel, their core collapses under the influence of gravity, and the outer layers are ejected into surrounding space at enormous speeds, at least 1/10 the speed of light. This phenomenon is known as a supernova explosion, as the dying star can emit light comparable in intensity to that of entire galaxies. After the explosion, a strange object known as a neutron star sometimes remains. It is very small, ranging from 10 to 20 kilometers in diameter, yet it is massive, between 1.4 and 3.2 times the mass of the Sun, and its density is practically equal to that of the nucleus of an atom, over 100 million tons per cubic centimeter. This star is primarily composed of neutrons held together by gravity and is not technically a star, as no internal reactions occur. A neutron star, possessing a mass several times that of the Sun and the size of a large city, creates an incredibly powerful gravitational field. In the vicinity of this object, the deformation of spacetime geometry exceeds the curvature caused by the Sun by at least 10,000 times. Thus, there are corners in the universe where one can observe specific effects of the theory of relativity in all their splendor. However, how can such small objects, located at impressive distances, measured in millions of light years, be detected? It turns out that the work of astronomers can be facilitated by one unusual property of these amazing cosmic formations. A neutron star possesses a powerful electromagnetic field, and, after the explosion that formed it, rotates very quickly around its axis, resembling a spinning top. The speed ranges from 1 to 100 rotations per second, and sometimes this spinning top spins even faster. Additionally, a highly magnetized neutron star emits a narrow beam of electromagnetic radiation in the radio range in the direction of its rotation. This is somewhat similar to the beam of a rotating spotlight. If the star's orientation is favorable, then the sweep of the beam, due to the star's rotation, periodically reaches Earth. An observer on Earth sees the pulsating radiation, with a period equal to the object's rotation period, like light from a distant lighthouse at sea. Because of this property, a neutron star is also referred to as a pulsar, short for the English term pulsating star. The very first representative of this type of celestial body was discovered in 1967 by British astrophysicist Jocelyn Bell. Currently, there are approximately 300 known neutron stars. Neutron stars are not always solitary. Since 1970, astronomers have discovered a number of binary pulsars, tight pairs in which two objects orbit each other in just a few hours. Binary systems provide an outstanding opportunity to observe certain effects predicted by the theory of relativity. Once again, as in the case of Mercury, scientists encountered the phenomenon of orbital precession. Recall that the precession of Mercury's perihelion, the movement of its orbital axis around the Sun, was found to be greater than predicted by Newtonian physics, exceeding calculated values by 43 arcseconds per century, which was precisely explained by Einstein's theory. The intensity of the gravitational field of pulsars is significantly higher, so their precessions are much greater. For example, the first discovered binary pulsar, and the most studied to date, has a precession of more than 4 degrees per year. In some binary pulsars, it exceeds 10 degrees per year. Once again, astronomical observations confirmed the predictions of the theory of relativity. At the same time, observations of a binary pulsar discovered in 1974 by Americans Russell Hulse and Joseph Taylor indirectly confirmed the existence of gravitational waves, as predicted by Einstein. They were directly registered only in 2015. By the end of the 18th century, scientists began to question, based on Newtonian theory, whether there exist celestial bodies so massive that they could retain the light emitted by them. the Englishman John Michell, years of life 1732 to 1793, and the Frenchman Pierre-Simon Laplace, years of life 1780 to 1827, independently discovered, with a few years' difference, that such black bodies must be hundreds of times more massive than the Sun. Later, after 1915, the general theory of relativity provided new data for studying this problem and investigating the behavior of light in a very powerful gravitational field. In 1916, the German physicist Karl Schwarzschild predicted that if a star's mass is confined to a sufficiently small volume, it becomes very dense and distorts the geometry of spacetime to such an extent that a situation could arise where not a single ray of light could escape. Furthermore, any object that comes near this dark star is immediately drawn toward it due to its immense gravity and cannot escape. This is why such a celestial body, which cannot be seen, was dubbed a black hole. The term spread thanks to the American physicist John Wheeler, years of life 1911 to 2008. By the end of the 60s, nothing could prevent matter from plunging into the heart of a black hole. It tends to concentrate in a point of seemingly infinite density, known as a singularity. The idea seems utterly astonishing. In a black hole, the distortion of spacetime reaches such a degree that the singularity is surrounded by a kind of horizon, a hidden boundary beyond which nothing can escape, not even light. This event horizon, separating the black hole from the rest of the universe, prevents us from knowing what happens inside, while crossing the horizon forever condemns one to the impossibility of escaping. The notion that a certain physical quantitative characteristic could reach infinity, such as the density of matter in a black hole, did not sit well with Einstein. In his view, such a phenomenon could not be a physical reality. It rather indicated errors in the theory. Even today, a significant number of physicists believe he was right. If quantum effects are taken into account, it may very well turn out that no singularity exists. Radiation could escape from black holes, or at least create such an impression, according to the patterns defined by quantum physics of a certain process, the existence of which was suggested by Stephen Hawking. Years of life, 1942 to 2018. Ultimately, from the perspective of strict theory, i.e., classical positions of the general theory of relativity, black holes should not exist at all. While these objects remain subjects of speculative speculation and heated debates, as well as intense research, many physicists believe that accurately describing such objects that simultaneously combine manifestations of gravity and quantum effects is only possible through the creation of a special theory of quantum gravity. Unfortunately, to this day, it still does not exist. After decades of debate, most astrophysicists are convinced that black holes do indeed exist, despite the fact that the existence of these objects was not predicted and did not fit into the general theory of relativity. Of course, it is impossible to observe black holes directly. Meanwhile, astronomers have also discovered sources of very powerful radiation in the X-ray range. This phenomenon appeared as a reminder of a black hole, invisible, and of course, with the mass of a star, that is, about the same as most stars, consuming a neighboring ordinary star. Recently, the existence of black holes of this type was vividly confirmed by the detection of gravitational waves. Additionally, there are groups of stars moving at very high speeds along strangely distorted trajectories. Scientists believe that the cause of the distortions is the gravity caused by a black hole, concluded by the process of elimination, as there is simply no other explanation. How could such monstrous objects arise? Undoubtedly, as a result of explosions of giant stars more than 10 solar masses, transforming them into supernovae. The collapse of a stellar core can lead to such density of matter that it becomes too unstable to form a neutron star, and, theoretically, nothing can prevent further collapse to a state known as a black hole. This is how stellar black holes with masses of several suns could form. It is possible that there are indeed many of them in galaxies, and they may be the sources of the powerful emissions mentioned. Calculations indicate that these may be very small objects. The theory suggests that the event horizon of a black hole with a mass equal to that of the Sun could be located just 3 kilometers from its center. Such a black hole represents a sphere only 6 kilometers in diameter. Of course, when viewed from the outside, the curvature of spacetime allows for the assumption that the internal dimensions could be immeasurably larger. Increasingly numerous and convincing observations show that in the centers of galaxies, including our own, there exist truly gigantic black holes, supermassive ones, with masses reaching several million suns. The process of their formation is not fully understood. However, they undoubtedly play a crucial role in the formation and evolution of these galaxies. For the first time, scientists were able to physically observe the curvature of spacetime in 1919 during a total solar eclipse. The image of a star was displaced in the celestial sphere due to the bending of light rays near the Sun. In the 30s of the 20th century, Einstein performed theoretical calculations of a similar situation for very distant objects. Light from them can be deflected by galaxies or galactic clusters encountered on its path. The result was quite inspiring. The distortion caused by large objects in the foreground of the observer can magnify the image of a distant object, just like a telescope lens. This phenomenon was named gravitational lensing. And that's not all. A gravitational lens can also distort and even duplicate the image of a distant celestial body. In this case, astronomers see something like multiple celestial mirages, displaced, distorted, and multiplied images of an object whose light was distorted before reaching the observer. According to observations, the first gravitational lens was discovered in 1979. Scientists saw a double image of a quasar, an extremely bright object located billions of light years from Earth. Starting from 1987, astronomers managed to discover numerous gravitational arcs, images of distant galaxies distorted by incredible masses and galactic clusters located closer to Earth. Sometimes these images are distributed around the lens and form a gravitational ring. Observing all these phenomena clearly confirms the validity of the theory of relativity. However, interest in gravitational lenses does not stop there. On one hand, they allow the study of distant objects that shine very faintly and would not be visible without magnification. On the other hand, analyzing the effects they produce, magnification, distortion, duplication of images, provides researchers with information about the lens itself, its size, shape, mass, and even, in principle, the distribution of mass within the object, even though it may very well be invisible. These studies help astronomers create a true map of lenses and discover invisible objects. The results of mapping seem to confirm that most of the mass in the universe indeed exists in invisible radiation in the form of dark matter, the nature of which remains unknown to this day. Regions of high mass concentration, galaxies and clusters of galaxies, cause strong distortions of spacetime, which deflects light coming from distant objects. As a result, we see them not where they actually are, and sometimes even in different places simultaneously. In the closer part of the cosmos, each of the massive and dense objects also creates its own curvature of spacetime, weak, but sufficient to serve as a microlens and create a small but noticeable distortion of light from a star moving behind our invisible neighbors. This effect, although it requires some effort for interpretation, could serve as one of the methods for detecting invisible massive objects around us in the vicinity of our galaxy. A few years ago, astronomers thought that the mysterious dark matter could consist of such objects, for example, small, very faintly shining stars and planets. They named them micromasses, or compact massive astrophysical objects. However, completely new research projects using those very microlenses showed that they constitute a very small part of the hidden mass of dark matter in the galaxy. This news was long anticipated, but nonetheless shocked the scientific community. On February 11th, 2016, the LIGO and Virgo teams made a joint announcement about the detection several months earlier, on September 14th, 2015, of the first gravitational wave. The phenomenon was coded GW 150914. The scientific community had no doubt that this event would occur sooner or later. It had been anticipated for almost 100 years. However, they were astonished by the speed with which the wave was detected after the installation of the detector and the power of the catastrophe that actually became the source of the waves, the merger of two massive black holes. Until then, scientists believed that such phenomena occurred extremely rarely. The discovery once again confirmed the validity of the theory of relativity, which predicted the existence of gravitational waves. Furthermore, it confirmed the reality of the existence of black holes themselves, which still continued to raise some doubts. The black holes turned out to be so massive that their detection opened a new chapter in the history of theoretical and experimental research. A new field was born: gravitational astronomy. The existence of gravitational waves was first predicted in 1916. The validity of the prediction sparked heated discussions among physicists. For a long time, it was believed that the disturbance of the gravitational field was negligibly small and that they were impossible to catch. Only a few enthusiasts continued to work in this direction. The LIGO detectors, Laser Interferometer Gravitational Wave Observatory, and Virgo, the French-Italian gravitational wave detector located at the European Gravitational Observatory. Hint at the Latin name of the constellation Virgo. One of the main goals of the researchers, based on the principle of laser interference, an idea that emerged in the 60s of the 20th century, was to create and technically implement the principles of specific technical devices, which took several decades. After the first test in 2007, the installation had to be refined for several more years. In 2015, the improved version was launched and almost immediately provided the first results. The astonishing prediction of the theory of relativity in 1916, shortly after the final formulation of the principles of relativity, led Einstein to predict the existence of gravitational waves, small oscillations of the curvature of spacetime that propagate at the speed of light and are somewhat reminiscent of vibrations in an elastic medium, as elastic as jelly. In this case, he envisioned space-time itself. 2 years later, he even published an equation describing this process. The publication sparked discussions, and it was debated that even Einstein himself had doubted his conclusions. However, in the end, by the 50s, the scientific community reached a consensus regarding the reality of gravitational waves. Oscillations of the gravitational field can be caused by sudden and asymmetric movements of very massive objects, such as the explosion of a massive supernova, the absorption of a very dense star by a black hole, or another black hole rotating in an adjacent orbit. The problem is that even extremely massive bodies produce only very weak waves, which are quite difficult to detect through direct measurement. In 1974, the first evidence of their real existence came from observations of a binary pulsar discovered by astronomers Russell Hulse and Joseph Taylor. The scientists studied a system of 2 neutron stars with an orbital period of 7.45 and incredible precession. Moreover, long-term observations showed that the period of the bodies' orbit around each other was constantly decreasing by 76.56 milliseconds per year, meaning the bodies were rotating faster and faster and slowly approaching each other by several meters each year. Theoretically, in a few million years, they should collide. These microscopic changes fit perfectly into the theory of relativity. The rapid movement of the stars generates gravitational waves that lead to a decrease in the energy of the system. This first evidence led to the awarding of the Nobel Prize in Physics to Hulse and Taylor in 1993. The study of other binary pulsars also proved equally convincing. Attempts to detect them since the 50s of the 20th century had astronomers nurturing hopes of capturing the elusive waves directly at the moment of propagation. This seemed incredibly complex, as any passage of a gravitational wave represents only a slight oscillation of the geometry of spacetime, provoking very weak fluctuations in the distances between 2 fixed objects. The expected amplitude of this wave, defined as the relative change in distance, was 10 to the minus 21st power. This corresponds to a shift of 10 to the minus 16th power meters between 2 objects located 100 kilometers apart, which is less than the diameter of a proton. The task was to detect these changes, however insignificant they might be. The first efforts to solve this problem were made as early as 1906. American physicist Joseph Weber, years of life 1919 to 2000, from the University of Maryland, built the first detector, which was a huge aluminum cylinder 2 meters long and 50 centimeters in diameter. It was expected that it would enter a state of resonant vibration under the influence of a gravitational wave. However, despite a number of claims later disproven, its sensitivity proved far too inadequate to detect possible gravitational oscillations. In the following years, some physicists recognized the potential of using laser interferometry to detect microscopic shifts. Around Professor Kip Thorne from the California Institute of Technology, a group of scientists formed to organize the production of gigantic detectors emitting laser beams over very long distances. According to the National Science Foundation of the United States, the LIGO project became one of the most expensive in the entire history of American science. Its budget equaled the cost of 1 hour of war in Iraq. Unfortunately, this detector works in cooperation with the European, primarily Franco-Italian Virgo detector, whose specialists were the first to announce the detection of a gravitational wave. Currently, two similar projects are also operating in the world: GEO 600 in Germany and KAGRA in Japan. The LIGO project consists of two gravitational interferometers separated by 3,000 kilometers. This distance is traversed by a gravitational wave in 10 milliseconds. One is installed in Washington State and the other in Louisiana, USA. The device operated from 2002 to 2010 and resumed operation in 2015 after upgrading the detectors to advanced 3G. Each detector is equipped with a special semi-transparent mirror that splits a superstable laser beam into two, reflecting the beams in perpendicular directions. The two reflected beams travel within very long arms of tubes 3 kilometers long in a near-perfect vacuum and are reflected in mirrors suspended at the ends of the arms to avoid the influence of seismic activity. Due to countless reflections, the beams of light traverse the arm's length multiple times, reaching a distance of 150 kilometers, and then they recombine in such a way that the interference process reveals the difference in path length between them. The idea of the device is that the passage of a gravitational wave should alter the path taken by one of the beams by about 10 to the minus 18th power meters, resulting in spectral lines shifting so that the difference between them can be measured even if it is infinitesimally small, smaller than the size of a proton. The main enemies of the experiment were noise, thermal noise, seismic noise. Only experiments in space are completely free from it, along with other parasitic noises that could significantly distort the results. Special technological solutions help deal with the noise. A gravitational wave, like any other, is characterized primarily by its amplitude and frequency. LIGO and Virgo are capable of registering an amplitude of 10 to the minus 21st power within a frequency range from 10 to 1,000 Hertz. Surface oscillations, seismic noise, prevent the investigation of lower frequencies. These figures indicate what phenomenon generated the gravitational waves detected by the detector. In this specific case, it could be the gravitational collapse of one of the stars in our galaxy, leading to the formation of a black hole. Such an event occurs no more than once a century, or the collision of distant but very dense celestial bodies, neutron stars, or black holes. The historic joint announcement was made on February 11, 2016, by the teams of the LIGO and Virgo projects. The registered signal fully confirmed the calculated event, namely, the collision and merger of two black holes with masses of 36 and 29 suns. The intensity of the signal allowed for the determination of the distance to the event, which was 400 megaparsecs, or 1.3 billion light-years. The black holes once orbited each other, but the emission of gravitational waves gradually drained their energy, and the orbit shrank until they collided, merging into a single black hole. Its mass of 62 solar masses became slightly less than the sum of the original masses of the merged bodies. The difference corresponds to the amount of energy carried away by gravitational waves. A beautiful illustration of the mass-energy equivalence equation, E mc2, as French physicist Thibaut Moore, one of the first to calculate the results of the observation, explained, "What we observed lasted only a moment. No one even had time to blink. The black holes had been rotating around each other for hundreds of millions of years, and physicists were able to register the last tenths of a second before they merged into one. The final rotations and the ultimate absorption. All of this was captured in the signal that traveled to us for 1 billion years. It should be noted that although gravitational waves are generated by gravity, they, in turn, generate gravity. This illustrates the nonlinear nature of the interaction, making calculations very labor-intensive, as described by the general theory of relativity. Scientists eagerly awaited this. First and foremost, the event confirmed the validity of Einstein's theory and the existence of gravitational waves, of which few doubted at that time. However, the fact of detection became a very eloquent argument. But most importantly, the registered signal proved that black holes are also quite real, and their special properties were even identified. We are talking about quite significant masses, 36 and 29 suns, while those black holes suspected of emitting X-ray radiation have masses no greater than 15 suns. Previously, specialists believed that supermassive black holes occur very rarely, yet the very first experiment detected 2 such massive holes, which cannot possibly result from the merger of 2 neutron stars, each of which has a mass not exceeding 3 suns. Theoretically, they should form after the explosions of supernovae with a mass of at least 100 suns, since only the core of the star collapses and turns into a black hole. Shortly after the first registration, information was announced that 2 black holes with masses of 14 and 7 suns, respectively, merged into one with a mass of 21 suns. All this led to a revision of theories describing the formation and evolution of stars, as it was previously assumed that such massive stars were also quite rare. We have the fortune to witness the birth of a new branch of astronomy, gravitational wave astronomy. The birth of gravitational astronomy, alongside new regular registrations of gravitational disturbances by ground-based detectors, has led specialists in this new field of astronomy to plan to move experiments into space, starting with the ambitious LISA project, Laser Interferometer Space Antenna, an advanced laser interferometric space antenna. This gravitational antenna is constructed based on the same principles as its terrestrial counterparts. It consists of 3 probes in a state of free fall, equipped with mirrors stabilized to a precision of 1 micron and connected by a laser beam. In interstellar space, there is no need to create long arms. The probes form a gigantic triangle with sides of 5 million kilometers, and a gravitational wave can significantly deform it. The noise compensation system in the probe's shells protects the mirrors from various disturbances, solar wind, cosmic dust, or particles, and so on. The technology was tested during a special space mission, Alice Pathfinder. It was launched into space in 2015 from the Kourou launch site and tested the working characteristics and reliability of the future detector. The triangular artificial constellation is expected to be sent into orbit in the solar system around 2030. The space detector will investigate a lower frequency range compared to today's ground-based detectors. For the LISA project, this will be a range from 1/10,000th to 1/10th of a hertz. It is anticipated that LISA will be able to observe binary systems of very dense bodies, black holes and neutron stars, white dwarfs, and gather data on the physical properties of black holes, and perhaps even on relic gravitational waves that emerged at the very beginning of the universe's formation. The sensitivity of the devices is such that their task is not only to detect sources, but also to identify them amidst the avalanche of incoming signals. The initial task of the mission will be to work with already known sources of waves, such as binary pulsars, to test the effectiveness of the technology. Observations of numerous other potential sources of gravitational disturbances are also planned. Special attention is expected to be paid to the merging of black holes already detected by the LISA mission. The new technology will allow for prolonged observations. Moreover, there will finally be an opportunity to accurately determine the location of the interacting bodies. In any case, the project will be one of the most significant steps toward creating true gravitational astronomy. Recently, scientists have also focused their attention on pulsars. These natural clocks and the registration of their signals have reached a high degree of accuracy. A group of several pulsars could serve as a natural cosmic detector of gravitational waves on a galactic scale, sensitive to a frequency range in the microhertz region. This could significantly expand the set of astronomical tools in modern science. In the near future, observations of pulsars will yield new discoveries in the field of gravitational waves. Additionally, it is also possible that relic gravitational waves were formed in the early stages of the universe's existence, for example, during processes preceding the recombination phase. This follows from many widely accepted views on the development of the universe. Primary phase transitions, inflation, the emergence of the first fluctuations, although modern physics is still not fully capable of understanding and explaining this. Theoretically, relic waves should have spread freely, gradually weakened by the expansion process, almost like the electromagnetic waves of the relic radiation, and they should have left faint traces in the background cosmological radiation. For instance, they could have altered polarization, properties characterizing electromagnetic radiation. Detecting these traces would provide scientists with access to crucial information. A statement by a group of American scientists about such a discovery in 2014 caused a stir, especially among those scientists who awaited confirmation of the cosmic inflation hypothesis, the presumed phase of super-fast expansion in the first moments of the universe's existence. Unfortunately, the results did not receive confirmation and were disproven.